Tuning is for reclaiming, for allowing the hypervisor to reclaim memory from your VM. So it's basically a cheap way of not having to interfere with the memory map on the VM.
So super silly question then. We have the dynamic capacity interface for CXL. If we had a virtual device for that, couldn't we just wholesale replace the ballooning driver and be able to just hot plug memory through?
I mean that's what VirtualMem does.
Yeah.
Right?
Okay.
But like Hyper-V, like so far did not implement a similar concept because I mean they don't implement Virtuo or something like that.
All right, we are out of time.
We're out of time, but that's a good thing. I will need to talk to people so that we can do something there.
Yeah.
Hello. My name is David Willer-Boyso. I work at Samsung. I've worked across a couple of topics in CXL, and today I'm going to be talking about CXL and back-end validation feature. I've divided kind of the presentation into like the general use cases that this allows in the theoretical sense, and then how it applies to some of the support we've added for Linux. CXL has three kind of coherency models for its host managed device memory. The first is the HDMH, which is the most basic analogous to system RAM, and where the host is the only agent in charge of dealing with coherency. Then these are like for type 3 memory expansions, for example. We have HDMD, which is the device traditional device coherent support, which manages hardware coherence through the CXL.cache protocol. And most recently, but not particularly new, as of CXL3, we have the device coherent model with backend validation, which is what we'll be talking about today. And with HDMDV, essentially the device has the responsibility of tracking ownership of its lines, and it does so through an inclusive snoop filter. And essentially you can do direct snooping on the device host caches or peer caches. And it uses two dedicated channels on the CXL.mem protocol. The BI snoop, which is from the device to the host, and the response, which is the host back to the device. The reason essentially this is done through the .mem and not .cache is to avoid potential deadlocks in the channels. Essentially, in these scenarios, lines can be changed by accelerators, near data processing entities, and also other hosts. This was introduced in CXL 3.0, and it requires operating in PCI flip mode, which is an enhanced way of unit of transfers going away from the variable sized that was before PCIe 6. So essentially this feature opens up a couple of interesting use cases for CXL. The first is leveraging PCIe unordered I/O, which was as a PCIe 6.1. And it basically allows moving away from tree-like topologies into having more of a graph-like topology with multiple paths. So in this scenario, before backend validation, the traditional way of dealing with these access patterns is that the host was always involved. It was always having to solve coherence. So now, if you picture a device accessing through UIO to an HDM region, type 3 device, for example, that request will not necessarily be routed to the host CPU, depending on the state of the line. So in this example, for the read case, when accelerator is doing a read to the HDM memory, it will not go to the host if it's invalid or shared state. It'll just route to the type 3, and the type 3 will do the return of the data. In the case where it's not an invalid or shared state, then the device will send a back invalidate snoop, invalidate that cache line on the host, wait for the response, and then return the data. Similar for the write, if it's in valid state, then again, there's no need to go to the host. The next use case that makes this very popular is distributed shared coherent memory. Essentially, if in this example, a host gets ownership of a cache line, and it's an invalid state, and it transitions to shared for a read, for example. Then another host 3, does the same. So at this point, in the directory of the switch or the fabric or MLD, it will identify that host 1 and host 3 have this line in shared state. But then when another host comes in, host 4, and it requests an exclusive copy, then the CXL device has to issue a snoop to invalidate the lines in host 1 and host 3. And it will only return the data after the responses from each of one of those snoops are provided. So it scales based on the amount of hosts that are actually sharing the line. The other use case is basically allowing accelerators to map larger regions of memory. This is CXL, and in CXL.cache, traditionally you had the bias flip between host and device modes. And in this case, you can essentially do larger mappings, and which was previously disallowed in that architecture through you could not do an inclusive snoop. Overall, these are the use cases, and explain kind of the events that trigger these back invalidate snoops. There are others. In the case when the snoop filter capacity is at a limit, and a new access is done, and it has to allocate a new entry in the snoop filter, and therefore it has to evict some old entry. You also have the use cases presented by kind of RAS operations, which will naturally be kind of like post-package repair, maintenance, and that requires the invalidation because it's part of the actual operation being done. You also have the confidential computing state changes, and when the state changes in the region, the BI snoop is issued back for all the affected addresses.
So the one I'll see on here, that one I'm kind of super interested in, is every time we change the HDM coder configuration, we get to flush caches.
Yes.
And right now we are on borrowed time doing x86 write back and validate. If you see Peter Z's responses to some of our uses of that, he's like, I don't like that. I mean, nobody should like that instruction. But the problem is you can definitely build a DCD device without HDMDB. But it'll be lovely if every time an extent goes away and comes back, we can have the device flush the caches.
Yeah, So
we're definitely interested in DCD and trying to put it on the list, right? To kind of push that forward and say, here's why we would want it. I think that would help, right? That definitely. So that's another way of pushing forward, because the whole thing for DCD for us was the fact that nobody wanted to change the HDM decoders is why we grabbed it, right? From, I think it was Plumbers a couple of years ago. It was kind of like a agreement, right? And so I think it's still hanging. So DCD is still hanging. So any way to push that forward, I think is good.
yeah, and what we have now, even without the write back and validate on all CPUs, the software approach is not ideal for obvious reasons. We want these hardware strategies, these hardware models, but there's also a question of like the capacity limitation is it's a finite resource. So at some point, there's probably going to have to be a compromise between hardware and software for coherence management. So those were kind of like really quick, the overview of the use cases that Back and Validate opens up for us. In my mind, my opinion, the peer-to-peer case is the most tangible one right now. And we started looking at how do we add support for this in Linux, really. And we have QEMU support out there. And this is a fairly, I mean, if you've been doing this is kind of your normal configuration. Just the green areas highlighted are kind of what changed. So for QEMU, we kind of had to split the support in two. First is extending the current PCIe support for flip mode, and then the actual BI support for the Type 3 device. For the root ports and the downstream ports, kind of it always presents flip mode, but the actual upstream ports and endpoints are the ones that kind of determine after the training if the topology itself is fully supported. And one thing I haven't mentioned is that, like, for Back and Validate to actually work at a system level across the entire topology, you need this support for every single point in the hierarchy, right? So right now, if you add, just for example, on the Type 3 device, flip mode and Back and Validate support, but you don't add it at the upstream port, the kernel will not work. We'll basically say you can't use BI. So with this support, we extended the driver to basically allow discovery and config and region provisioning support for this. My hope was to, in a single call during probing, whether it be type 2 or type 3, you can essentially determine the coherency model that the device is currently on. This is a mix of using the CXL device state for the type, and then after the discovery or the BI setup, really, you would know with a simple BI flag whether or not it's supported. And again, this support is required. It requires the whole topology to have the flip mode support, and as well as the endpoint device BI support itself. So after a successful discovery of Back and Validate, the current logic, the current support is strictly for Type 3, and the expectation is for the user to create regions through sysctl, but not automatically, and basically allow your extending in small amounts the current provisioning support. While Type 2 support would be obviously created through the driver that's making use of it. For the like on removal, the one requirement is that the device be offline and or unmapped for deallocating the BI ID, which is like just the identifier of the device supporting it. So this is the example of how Type 3 devices can be, regions for Type 3 devices can be created with back and validate support. A single device can have different ranges supporting BI, or it can support regular HDMH or HDMDB in different parts of the device. So creating the regions based on this is it's a nice way to separate the different coherence models on the same device. And this is kind of where I want some community feedback as to whether or not this is a correct approach for Type 3. And essentially, once the root port decoder, like from the CXL window, it has no BI restrictions. We have a BI capable device, endpoint device. We can take a very similar approach to like the volatile or persistent memory region creation, and it's all is done for the user. All the user has to do is to basically once we know that the BI is supported, you just set the decoder you set the BI flag on the decoder, and you basically create the region and you commit the decoder. This has to be done. It's if we detect BI support, we do not auto online the memory. That's necessary because upon probing, upon the discovery, we don't know, we cannot assume that the topology itself is BI friendly. So we can't auto online BI regions because we don't know the rest of the story and for the rest of the hierarchy. So some discussion points are like, we have this functionality now. Where do we go? Where do we go with it? Right now, there's Type 2 support and CXL.cache work posted upstream. My hope is for once this is upstream, to be able to integrate it, to be able to integrate the BI support with the discovery functions. But that's like, I don't know if there's been no real hardware announcements for that. Not even much announcements in regard to accelerators at all. So that's an open question. Like after the Type 2 and .cache support, can we continue adding the BI stuff? The fact that the UIO is an essential partner to back and validate in many ways. There's no support for that. Do we want to add support for that? Again, there has been no hardware announcements related to this sort of thing. And what for the distributed memory, the coherent distributed memory cases, how can we best, what are the most like tangible ways of leveraging this? Right now, my initial guess would be maybe FAMFS.
Oh, I thought you were gonna say like that we should go talk to the peer-to-peer DMA people, because like that subsystem is growing and getting more attention, and it feels like what we want, if somebody builds an accelerator with this, that we're going to want to figure out how to, because right now that's based on MMIO bars, and you want to be able to say, hey, I want to, this is my accelerator PCI device, give me the CXL region, memory region that I need to do my whatever my peer-to-peer DMA stuff is.
just memory. Right?
Comment on it, it's just memory, but I feel like we still have to do the association somehow. Like we still has to be like this device needs to talk to this memory, and here's the address. But yeah, you're right. It's not actually peer to peer. That it's just memory.
Would say that this should be backend validation, like from the software model. The backend validation is necessary on the.
Yes.
That's a given. But the thing is, the software model should not caring if it's L or whatever data fabric you have below it. That can
Yes.
transparency, right?
Yes.
The main problem is at the moment if you tie this all to CXL, great, but it's also like then limiting what CXL devices define it. Right? I think have a more general solution.
Correct. Yes, and that's why I say that like the discovery and the region provisioning kind of logic is strictly for CXL. But yeah, it like from a software usage standpoint, like it should make no difference.
Regarding the type 2 support, CXL cars and all of that, I think so what AMD is doing, another guy, not me,
yeah,
is about the CXL cars when the host cache, sorry, the other way, when the device caches host memory.
Yes.
And this is the other way.
Yes.
And I think for avoiding complexity, both works would be integrated upstream, because if not, the budget is going to grow to a significant amount. So I will be talking about the other way in the child.
Another kind of point of like discussion would be the DAX region semantics. Currently, in your series, you're basically preventing region creation for yeah. No, we can't hear.
Jonathan, do you have a question?
Oh, okay. Sorry. Yeah, just to point out, there's another case in the spec which we do also need to handle, which is accelerators doing.
We don't have audio from you, Jonathan. Sorry.
Okay.
Type it out, and we'll continue here while we wait for it.
So essentially, right now, for accelerator memory, DAX is not supported. Right. So I noticed like there are cases like for sharing where you for type 3s you would want support for this. So decoupling the UAPI from the coherence would be is kind of like I kind of want to know if that's still on the table, because if it is, that would actually have to also be maybe a requirement for the type 2 support. Yeah. So yeah, last but not least, so something like what we were discussing at the beginning, the current mem region invalidations we have has always been the worst case scenario, whether it be the ranged flushing from ARM or the x86 big hammer we have currently. These are kind of open questions. Like there's a lot of research that points out to like combining the hardware strategy for coherence management with the software one. The larger the snoop filter capacity, the more costly it is. So there's a balance between the amount of overhead incurring in a miss and in a capacity miss versus the cost of the device. And again, I think these kind of things will only come clear with time. but they're like at some point I would like to like not have to rely on the memory region and validation stuff, but I really don't see that happening. Let's see. Yeah, lastly, yeah, as I was saying, there's a lot of research showing that showing numbers right now without back and validate support, and they conclude that this is kind of really the numbers will only get better with this.
And there's another argument, something which we pointed across onto our talk earlier on. That will get us away from the problem of bandwidth restriction on the uplink.
Yes.
Because the biggest issue which we currently have is that we are bandwidth limited. As soon as we have this, as you have a CXL switch, you are essentially bandwidth limited on the uplink between the switch and your system. As there are several PCI, potentially several CXL devices on the switch itself. So you always have the bandwidth limits, which is something which we currently cannot reflect in our topology. We always assume latency is the key indicator here. But if you're bandwidth limited, it is not, because suddenly both measurements are getting skewed apart, like he showed. And that is something we can't really measure. So we cannot accommodate for it, even if we wanted. So having this would get us away from, because then the bandwidth on the uplink isn't that important anymore. You can do peer-to-peer or essentially peer-to-peer memory within the switch, which is really what we need.
Yes, you save bandwidth and you improve latency by avoiding the host, of course.
Your comment about not getting away from the memory region flush stuff. I mean, like, correct me if I'm wrong. You did an experiment where you switched from write back and validate to CL flush, and it took 30 minutes or something.
Oh no, that wasn't write back and validate. That was just moving from. I'm sorry. I was thinking back and validate. Yes, from write back and validate to CL flush with the proper barriers. It took for 2 gigs. It took like a minute to create a region, and that is at first I thought that was without the recent QMU improvements, but then I discovered it was with that. So because we're at the range we're iterating on a cache line granularity 64 bytes, it gets scary. It gets really scary. And Hans Anven, HPA, he was mentioning that for terabytes you could take hours. So while it's lovely not to disrupt the whole system with the big hammer and keep one CPU busy, at the end you can't really wait hours to do this sort of thing.
That is true, but the sinister way of looking at it is, hey, hardware people, give us back and validate. Otherwise, we're going to flush you for an hour.
That's exactly it. Yes. Yeah, that's all. Mm-hmm.
So thinking from an accelerator perspective, so type 2 accelerators, at least from my opinion and experience so far, we're not terribly excited about CXL3 with PCIe 6 because of all of the benefits that you're getting of building an accelerator. You lose when you go to PCIe 6 with the transceiver changes, but this might make it interesting. So getting support tied to type 2 devices actually, I think, would be pretty important.
Yeah, the PCI constraints for bandwidth are always unattractive in this scenario, and
but it's also the latency, right? That's the really hard part, is the latency changes for the transceiver changes in PCIe 6. It's just unavoidable.
Yeah, and as in my opinion, as PCI generations that continue to evolve, there's going to be a point where the PCB design is going to be too complex, too costly, too much heat, and we'll have to find it's a big question as to whether or not CXL will survive through PCIe. But in my opinion, that it is back and validate is, if it's going to survive, it is one of the fundamental features, characteristics of technology in CXL that will make it happen. With without it, really, we're kind of like I see no future. I see no scaling future without it. For the easy direct attached scenarios, that's fine. But if we were talking about truly scale out fabrics and accelerators and peer to peer, and you need this. Thank you.
And yep, there you go. Off you go.
Hey, good morning. My name is Bharata. This is device-specific micro conference. Okay. Yeah. So as I was saying, right, this is a topic which requires plumbing from the Linux core point of view, but I'm kind of taking it through in the device-specific microconference. So I'll be discussing more about the ways and methods required for us to collect the hotness information from various kernel subsystems and trying to do a reasonably good promotion out of them. So the idea is to have a centralized subsystem within the Linux kernel, which acts as a single source of truth for the hotness information. So we have been discussing this idea for a while now. I first discussed in the LSF and based on the feedback, we have been continuously discussing in alignment calls. So today I'll be kind of discussing the further progress that we have made and some of the results that we have obtained. So quickly recap to the actual problem. So as I said, right, there are multiple subsystems within the kernel which kind of know about the memory hotness information or kind of detect the page hotness information. For example, we have specific NUMA balancer, which does the dedicated job of this. And then we have subsystems like LRU subsystem, which in a way kind of look at the page access bit and kind of look at the memory hotness information. Then there are upcoming subsystems which are capable of providing with the same information. Example is there can be platform provided hints like AMD IBS, or there can be other hotness information coming from the device side or the CXL side, for example, CXL HMU. So the ask is if it is possible to kind of consolidate all these things and have a centralized view of the hot pages within the subsystem. Another reason is that we already have the NUMA balancing, the hot page promotion tied to NUMA balancing or the scheduler. Is it possible to kind of delink it and kind of make a separate subsystem out of it? That's one thing. The other thing is about how about having a centralized migration thread or a migration subsystem whose sole job is to kind of figure out if it is provided a set of hot pages, just do that migration to the required node. These are the motivators behind this work. And this is roughly how the subsystem that we are designing looks like. So on the left-hand side, you have various possible sources which have just listed. NUMA hint faults is the existing mechanism. Then you have PTE A-bit scanners. These are all out of kernel under development. And then hardware hints, as I said. Then there are other subsystems like the routine named folio mark accessed, which kind of detects the access to the folios. Then there is the CXL side of things coming in. So all of them are expected to feed this information whenever they detect access to this centralized subsystem that I am developing and named as page hot subsystem. And there is this kernel thread that is kmigretd on the top right-hand corner, which the page hot subsystem collates information from all the sources, kind of maintains information about the hottest pages. And kmigretd subsystem is a kernel thread or a daemon which regularly extracts out of information about hot pages and does the required migration. Then there is a small other part that can be done, which is not yet developed. You could use the hardware acceleration, the DMA engines, etc., to do the offloading part. That's the idea. And some brief about what this subsystem is right now. How does it look right now? So it's a small subsystem. The core of this is an API that it provides, which is PG hot record access. Any subsystem which kind of knows about page memory access can use this API and report that access to this subsystem using the PFN as the base and the node ID where this from whose perspective this page is hot. Then there is the source identifier based on the multiple sources that I mentioned about. And finally, the time of access. So if you have this information, or rather if any subsystem has this information, this can be fed to this PG hot subsystem. What it does is it maintains per PFN information about the hotness. Right now, what I have is I'm using an unsigned long variable, the machine word length variable, to record information for each PFN. And this sits together within the memory section structure that we have, which describes the physical memory layout section wise. And I maintain this information only for the lower tiered memory, that is for CXL and other kinds of subsystems. So if you look at the memory overhead that we are talking about, this is one unsigned long per page, and it for x86 considering 4K pages and section size of 128 MB, etc. It amounts to around 2 GB per TB of lower tier memory. That is, it is 0.2% of the thing. And what we store as part of hot page record is in this right-hand lower corner. I don't know if it's clearly visible. Even I am not able to clearly see it here. That it is we have the node ID recorded. Then we have the access frequency recorded. So every time a subsystem reports the access, this access frequency is incremented. It's a 3-bit field. 8 accesses can be recorded. And then there is the time which keeps continuously getting updated. So this frequency and time, both of them are used to figure out how hot is the page. And finally, there is the last bit, or the 63rd bit, which is an indicator set by the PG hot subsystem based on the current setting. If it thinks that the page is ready to be migrated, that is ready to migrate bit. And the kmigretd kernel thread continuously scans the memory section and tries to see which of these have been marked as ready to migrate. And based, it extracts the node ID from that and migrates that page to that particular node ID. So the hotness is determined by the PG hot subsystem and extracted the information about that is extracted by the kmigretd subsystem. Any questions here? This is roughly how.
Pixel device tracking, for example, may be at a gigabyte boundary, right? Here, let's say the kernel is doing things at a 4K boundary. So how do you sort of make sense of different things are measuring at different granularities?
Yeah, that's. I thought CXL will still be able to provide you the hotness information for a range of pages, right?
But it's up to the device, right? Like the granularity is up to the device to implement, right?
Mm-hmm.
It may not be it probably won't be 4K, right?
Okay, but from what I understand, CXL HMU, it would provide you a list of pages, right, for as a hotness information.
No.
Okay.
Yeah, my
The comment was correct that it depends on the device, but if the device is sufficiently rubbish, we won't use it. People will build better devices.
my understanding of the HMU, I could be wrong, is that it's somewhat configurable on alignment, but again, as Jonathan said, definitely depends on the device.
Yeah.
Yeah,
So essentially,
it reports what it can do. Sorry, go ahead.
yeah, go ahead, Jonathan.
I was just going to say it reports what it can do. So if it's a good device, it might do 4K. If it's a rubbish device, it might not.
So there is this whole spectrum of things, right? Do you want to track it per PFN granularity, or you want to track at a region granularity, which is what Damon, the DAMOA and Damon provides. So here we have chosen to have that because the idea, the way we started out was to have an alternative implementation for the existing NUMA balancer-based hot page promotion. That is the tiering mode of hot page promotion, where things are tracked at page level.
It's also worth noting that the HMU, some of these mechanisms track physical addresses rather than virtual addresses. So the contiguity of a region isn't necessarily descriptive of anything in particular. So it's a difficult problem, but
So yeah, I'll just skim through some interesting facts about the different sources that we have. So we have this NUMA hint fault based mechanism of hot page promotion, where the address space is periodically scanned and NUMA hint faults are generated. So what I have done is I have used this as a source for PG hot subsystem. The address space scanning and the NUMA hint faulting mechanism remain as they are, but the when the NUMA hint fault comes, you kind of feed that information to the PG hot subsystem. Earlier, you used to take the migration decision there, but instead of that, that is handed over to the access information is handed over to the PG hot subsystem, and that kind of and other thing that is done is the TPP, as Gregory mentioned earlier, right? That's the core of this hot page promotion. The hot page heuristics, the thresholding part, the bandwidth rate limiting, that is all part of that new hot page, the NUMA balancer that has been extracted out and made part of the PG hot subsystem, so that the same heuristics will apply or can be used for all other sources that are kind of providing the hot page information. So that's what I have done. Hint faulting mechanism remains, but the bandwidth heuristics has been moved, and the hotness information is reported to PG hot, and PG hot will do the subsequent action of determining the hotness and transferring out or promoting the pages. That's what I've done with NUMA hint faults. Then there is PTE access bit scanning. This is one thing that we have been looking at for some time now. One of the things that we understood or kind of thought about is that this NUMA hint fault mechanism itself is kind of runs out of process address space. Migration is done in the process address space, so there could be latency issues or latency spike issues. So one of the alternatives that was suggested was to look at the PTE bit mechanism as a source of figuring out hotness, and there are two approaches that have been proposed here. My colleague Raghavendra has done this quite a bit of work on this approach called KSCAN-D, where he's maintaining a list of MMs, going through each of them periodically. He has developed some heuristics to detect the top tier to which the particular page has to be migrated to, rate limiting, per process opt-out, etc. It's a complete thing by itself, but it can actually feed information to PG hot. And then there is another implementation which is lean and mean and a little bit experimental at the moment. It is called KLRU Scan-D, which is done by Kinsey Ho of Google. RFC patches exist, and he is hooking into the MGLRU's page table walk. He has exported a callback for that, and using that in the kernel daemon, which is being periodically invoked to extract hot page information and feed it to PG hot. So this essentially is giving you information about hot pages as and when MGLRU kind of figures it out.
How do either of those work with larger page mapping?
Yeah, so it's all transparent because we, even though I say it is per PFN, right? So at the core of the thing, it is at what granularity are you migrating? I'm kind of looking at the folio, map back the PFN to the folio and kind of take it out from there. So if a PFN belonging to a THP page becomes hot, it gets tracked at the folio level and you would migrate the folio itself. Correct. Yeah, for that.
What does that inform about the hotness of the PFNs of that folder? Like, how do you say all the pages are hot within that range?
No, I'm not going into that level. If any of the PFNs within the THP 2 MB range or whatever range is hot, we figure out that, okay, the entire THP is hot and needs to be migrated.
Typical granularity issue, right? You lose accuracy as you track larger granularity things. It comes with the territory. I had a question regarding scalability, a bit of a loaded question.
Yeah.
How scalable do we expect the scanning mechanism here to be as systems become 2, 3, 4, or 5 terabytes in size?
Scanning by the K-migrate subsystem?
Yeah.
I'll come to that. I have a chart showing that.
Okay.
Yeah. Yeah, so this is a brief about, I mentioned about platforms which are able to provide you that hints, right? AMD instruction-based sampling is one example. So what it does is it hardware has the feature to kind of figure out the accesses and report back via some interrupt mechanism to the software or the kernel. And IBS, I have written a ARC-specific IBS driver which is able to extract and give that information. And that itself nicely fits into into this infrastructure, and it is able to give. It's a sampling-based technique. It has its own limitations, but it is an additional source. And then this is the whole work is experimental, and this part is even more experimental compared to that. So just recently, I kind of got this folio mark accessed routine to feed information to the PG hot subsystem. This kind of helps. Gregory was doing work on this earlier, where he had some approach to promote unmapped page cache folios, and this kind of helps to get the hot page information from that class of pages and kind of promote them. I have some early numbers from this. So those are the sources, and then we get to some numbers.
So I going back to source one, the NUMA fault hinting stuff, and this applies to the actual logic as to like where to promote. What are currently the ways you're deciding the destination node? Because here it's very nice because we always know, right?
Yeah.
Yes. My concern is, okay, you move it. Will you always need NUMA balancing 1, essentially? So if you get it wrong, you place the page in a node with compute with CPUs, but you're still not doing local accesses, local node accesses. Will you rely on NUMA balancing, moving that to the node, the compute node that is local, or?
Yeah. So very good question. Actually, it's been a very open-ended question, and we have been discussing it for some time now. Some sources provide you that information precisely, like NUMA hint faults, and the hardware hints like IBS, maybe CXL HME also. I would understand, but other sources are not that.
Not those.
Not
yeah.
okay. Okay.
And the thing is, if you get it wrong, you're going to be very wrong. And it's better maybe not to even promote in the first place. But then if you can fix it.
I wouldn't think it would be very wrong, actually. I mean, if you look at the latencies these days, I don't think it is like that wrong. It would be that different. It's a cross node.
That will be system specific, right? One socket system, you're always going to be right. Right. But this is where we get to, right? Yeah, but so it depends on the number of hops, depends on what the actual latency is. Like, so it's hard to know unless you have sample systems. Like with the actual cost of taking a double fault of, promote one time and then promote the second time, it might be negligible. It might be okay. It depends on how often you get it wrong, right?
Yeah, but the question is valid and the solution is open. The problem is open. Basically, PTA bit based mechanisms don't inherently provide you that, and as I said, right, case candy mechanism has some sort of heuristics to figure out, again, based on the scans that it has done. If NUMA balancing mode 1 is there, even better, but we will have to look at.
I'll offer one last thing, which is you will get better bandwidth, regardless of where you promote it to. So that will just be better.
Yeah, so that's one thing. The results, let me take you through. So the first disclaimer is that I'm not trying to kind of prove that this is that much percentage better or something. Basically, the idea is this is a subsystem that we are developing and kind of trying to prove that it kind of matches with what we already have, because this is not a subsystem which is trying to do things better in a sense over what the source already does. It is about combining the sources and evaluating whether we are in a position where it kind of matches to the existing things. We are not adding overhead to the entire mechanism. So if you look at this case by case, right, this is a promotion only case where the top tier is not kind of memory constrained. There is a lot of memory in the top tier. And the benchmark is a multi-threaded benchmark, a lot of threads running on the top tier and having provisioned its memory on the lower tier. And it does a lot of memory accesses randomly and repetitively. So in this example, I have an 8 GB of memory provisioned and lower tier, and it's completely random, 512 iterations of accessing each page in that 8 GB range. And each iteration is the page to access is random, basically. So everything randomized and predetermined, basically, so that the timing doesn't consider that randomness aspect. Everything pre-decided, you just go ahead and start touching these things. And the lower, the earlier that application completes, the better is it. Sometimes, yeah. So if you look at the base case, right, NUMA B0 is the case where I'm referring to, where there is no NUMA balancer at all. NUMA balancer has been disabled or not enabled. In that case, if you see 118 seconds is the number, and if you look at the PG hot subsystem, it's kind of there. So which kind of tells us that we are not adding any major overhead. When we say for the NUMA B0 case for PG hot subsystem, subsystems are there, they are reporting, but PG hot subsystem is not taking any action. So sources have been kind of disabled from the PG hot subsystem point of view, but your reporting is continuously happening. So that's the number you have. And NUMA B2 is the actual case of hot page promotion. And we are kind of there. So more or less matching with what NUMA B2 does. And I have a condition star there because in the current hot page promotion mechanism, the promotion happens on the first access if it is possible. But in the PG hot subsystem, it's a frequency based. So I have kept the threshold at 2 accesses. Twice access within a window will qualify the page for promotion. And hence, if you do that, there is a slight delay to detect that accesses. But otherwise, in the numbers that I have in the chart, I've just modified the threshold to be 1 so as to make apples to apple comparison, and we are there. PG hot subsystem is kind of really aggressive. We need to tune PGT scan that I have said here refers to the PT A-bit based scanning mechanism. And specifically, I'm using the KLRU ScanD from Google, which is kind of very aggressive, and hence other results will show some sort of regression, but we are kind of doing not so bad there. And hardware hints, of course, does a lot better, mainly because it's little difficult to get a benchmark which kind of exactly shows that benefit of having done so many promotions. I've not been able to get that the sweet spot right. Because of that, if you see, even though hardware hints, that is AMD IBS based sampling mechanism, is able to provide you only so many accesses, right? The overall the benchmark benefits because you are not doing so many migrations. So there is that sweet spot which kind of determines how fast you detect and versus how many pages you detect. And this is this exactly same scenario, except that instead of accessing the anonymous memory, I'm accessing file-based memory, which is mapped. And that kind of also shows you similar results. except that PGT scan, I have to figure this out, why it is kind of consistently doing much better compared to the base NUMA B2 case. It's a file access here. And this is the case where I think it would be more practical, where you are constrained on the top tier node, and your environment is doing both demotions as well as promotions. That's the reality. I would assume that you would want such a thing to work correctly, right? So here what I have is a benchmark where the memory is divided between the top tier node and the bottom tier node in the ratio of 75 to 25. 75% of the memory, which is 160 GB currently in my system here, is provisioned on the top tier node and not touched. And the remaining 40 GB is provisioned on the CXL node and continuously touched in the manner that I mentioned earlier. So the idea is, and I divide the memory into 1 GB stripes so that you continuously generate accesses to that 1 GB chunk, so that to build a notion of hotness within that region. And you expect it to be promoted, and for the promotion to happen, the demotion first should happen first. So results is kind of not very, it's kind of mixed result I'm getting. In the NUMA B2 case, right, many a times, I don't know if this is an issue, we need to kind of investigate a little bit. It is not even able to do any promotion at all, actually. If I see number of pages that get promoted in the existing NUMA B2 case is 0, whereas PG hot for some reason is able to detect, and in the NUMA B2 case, but PGT scan is able to detect more number of pages, that is KLRU scan D based mechanism. And there are a lot of things going behind here, promotion and demotion. It's not as easy as unconstrained system here.
I'm curious, what's the policy for when the on the nodes you want to promote to, if there's free space for that promotion to happen? Are you just verifying that there will be free space and then doing, or and if not, you don't bother?
Correct.
Or is it more aggressive with reclaim?
It is the same hot page heuristics mechanism that we have in the existing, where you will do promotion if it is not constrained immediately, or you would apply that bandwidth rate limiting and etc. And parallelly, you would have this reclaim based demotion that will be happening.
But the reclaim would come in a natural way upon allocation.
Yes.
Yeah. Oh, you can do proactive too, but it's not part of the promotion heuristics, the algorithm.
But it is part of the hot page heuristics, which will kick off that at a lower right.
But the number of pages promoted is not always a virtue, right? Like that.
Correct.
Okay.
Exactly. That's right. Yeah. That's what sweet spot I'm telling you. I'm mentioning about. I'm used to moving around actually. So yeah, I'll stand in the last remaining 3 minutes. Yeah. Okay, so quickly, Gregory mentioned about this, right? So we are looking at the rate of migration with respect to K migrate D here, right? The blue one here is the second line is the base NUMA B2. This is how it detects those accesses for the benchmark that I mentioned in the first. And the red line is the NUMA B2 driven by PG hot, where I am doing first page promotion. And the violet one, or the last to the right, is the one that is for NUMA B2 if I leave the frequency threshold at 2, that is the default for PG. You can see that there is a delay. And for the green, the PGT scan, LRU scan D mechanism is quite aggressive, I said, because this is how it kind of detects. So this is how the rate of migration looks like. And yeah, so you are mentioning about the overhead part, right? So in the version 3 of the patch set, I was scanning all the PFNs in the lower tier for looking for the hotness ready bit. But in the version 4, I have the hotness indicator per section, per memory section. That kind of hugely makes a difference, because if you see here, right, when the migration starts, in the first case, right, blue case, there is always a delay because you have to walk so many PFNs. But in case of the PG hot subsystem, it's kind of improved. Yeah. Yeah, this is briefly how unmapped page cache folio migration looks like using FMA or the folio mark access. There is definitely an improvement, but there is also a regression in the case where it is disabled for PG hot. So there is a lot of things happening underneath. Need a bit of analysis here.
Are you intending to have toggles as to which of these different hotness?
Yes. Yeah.
And then are you going to allow, the example of the unmapped page cache folios using folio mark access?
Yes.
Are you going to allow for different thresholds per feature? So X number of accesses from folio mark access is treated differently than X number of accesses from hotness monitoring unit.
We probably have to do some of those kind of things. It is all very basic and simple. I just like get accesses and deal with it. So, but yeah, makes sense. Yeah.
Okay.
Thank you.
So now we have a 30-minute break. We will start back up promptly at noon.
And I think that was the reason
Testing.
Can't do that.
Yes, I was just gonna say.
Yeah.
Internal policies.
So because then the region. Yeah. That's what I say.
Went to the hotel and I realized I couldn't check in before 3. What's their name? I thought that the dinner was ready for me. Yeah, but like the thing is someone is only like and like it was at the hotel, Canada told me, like wanted to get just wanted to sleep, but then my partner for 6 years better than what like work.
Not from the last one.
It's like another 6 hours. That's the same time next week. Like if when the flight back, it's going to be 14 and a half. think it has to do with probably because they have to avoid. I'm also staying in, but I think it was the one that you gave to me.
Well, I think Dan pointed out, I mean, I don't know.
Maybe because it's it's still okay. I think I need you most of the moment. Maybe it's the story for this, that's probably more. AI for does not really. But you probably attend the evening event. Next session on the 5th. I mean, I'm co-hosting it, so I should, because I think it starts at 3 p.m. Great. Oh, hi, ma'am. Yeah, this is. Yeah. It's probably next year. Let's think for you. You look at something and then you go.
Yeah, it could be.
Whichever one you want to do.
Yeah, it's-
So if you use the stay in front of the mic.
Okay. Yeah, sure.
Okay. Okay, welcome back from the break. Interest of time, we'll go ahead and get started, and people will filter in. This afternoon session is going to be a little bit faster paced, just to fit all the talks in. So please do give the presenters your undivided attention. And Alejandro, go ahead, take it away.
Okay, thank you. Well, hello everyone. So my name is Alejandro. Maybe some of you recognize my name. I'm that guy trying to get type 2 support upstream. While type 2 devices imply CXL MEM, that is what that current ongoing work about type 2 support is about. And the second part is CXL CAS. So this talk is about some concerns I have about how to support CXL cache. And this is the goals I have to share those concerns and make other people aware of these problems. Maybe they are just in my mind, but anyway, I think they are worth to discuss. Then to discuss with what could be done and identify work to do follow-ups. So yeah, type 2 devices imply CXL MEM and CXL cache. Type 1 devices imply CXL cache. And first of all, there's clarification that needs to be done because CXL cache imply or could be understood that we do two different things. One is CXL, a CXL device caching host memory. The other one is the host caching device memory. Okay, so this last one is what that talk about HDM DB was before about Davidor, and mine is going to be about the first one. Okay, so CXL devices caching host memory. So the thing that needs to be done by the kernel is not too complicated. So there's a snoop cache per host bridge, CXL host bridge, And then the kernel will look at the CXL device DVSec registers advertising CXL cars, and apparently the only thing to be done is to check that CXL cars advertised is less than the snoop cache size. So then the host can enable type 1, type 2. As you can see, I'm not mentioning here the firmware or the BIOS doing things with this. I'm not sure how that is going to work. So the first concern is about the base tracking. So first of all, I guess the host needs to know how many CXL devices with CXL cache are using the same Snoop cache, and not to allow not to allow CXL devices that are going to use more than the available CXL cache. For that, I'm not sure how the hardware is going to work in this regard, because with per device hardware tracking, I mean, the way these devices are going to use CXL cache could affect other ones. Maybe the hardware is clever enough for avoiding that problem. But being honest, I don't know. I am from one of the hardware vendors implementing this. So this is information that is hard to obtain. My feeling is that all of this is being implemented initially as the functionality, and all of these details are not being implemented, even discussed. But I think this is important to know. From the host, that is just one thing that we can do, is just to be sure that the hardware is doing the right thing, or is tracking this kind of potential devices doing the wrong thing, and then just to limit the number of CXL devices using CXL cache per Snoop cache. I don't know if we can do anything else, but at least we should be aware of this problem.
But the host can limit what a device, whether a device can cache or not. But that all comes back to this kind of awkward policy we have around whether a device is trusted or not.
Yeah,
like
this is the second
ATS. Okay, okay.
This is the second part, probably the more important. I think there's nothing that we can do here from the host. So, but at least we should have some way of okay, we are going to support just one device, but we are going to support that well. Yeah, what Dan was talking about is probably more concerning, and this is about how a CXL device can use CXL cache. For that, it will need the physical address to work with, or the IO virtual address to work with if IOM is in place. And well, usually devices for this kind of access to host memory, they use the kernel API for getting those addresses to work with. They allocate memory, and then they get the memory, the physical or the IO VA that is going to be used by the device. In this case, I think the DMA API probably is not needed, or well, that's the point about this, because there are other apparently restrictions about what a CXL device can do with CXL cache. Apparently, not all the CXL addresses, or not all the addresses, can be used from the host. That is from the specs that is specified without IOMU, and then with IOMU and virtualization, I think that the problem is far bigger, and probably is the biggest concern. So, because all these limitations about what a CXL device can use in terms of the physical addresses to work with, well, one question is if we need to change this DMA API. Note that a device will require DMA addresses as they do now, and then they will have these DMA addresses specifically for CXL cache or not. I don't know. So this is one thing to discuss. Some clarification maybe from the specs, or maybe hardware vendor saying, okay, you have these limitations. So when you allocate DMA from the kernel to the device, you need to be aware of this, and then we need to implement that. So depending of these requirements, well, I don't know how is or what is the best way to do this. Extending the DMA API, creating a new one, a wrapper. I don't know. Yeah.
So I'm trying to understand what the end result here is. Is it that you're trying to give information to, say, the host OS whether or not your device can cache, or because at the hardware level on an endpoint device, when you're dealing with .cache, it's all opcode between hardware and CPU and cache home agents. You know, the OS has absolutely zero clue that's happening. So I'm trying to figure out, like, what exactly are you trying to solve?
There are two problems. If you don't put virtualization in place and you don't have IOMU, then probably it doesn't care. I mean, it doesn't matter. You just trust the device can use the DMA addresses. And if we don't have any other kind of requirement about which CXL addresses to work with, that's fine. Okay. What I'm saying here is that from the specs, it says that those CXL addresses to work with cannot be or are not the same, or that they have some restrictions. Yeah.
Actually, two aspects here, right? Like typically, the main problem that I think what you're dealing with is that a lot of that DMA is happening at the system space, right? Whereas if you do virtualization, you have actually the guest physical and the system physical. And so typically, like in the CXL model, you're pretty much operating on the physical address only. If you have like a mapping that is in the guest virtual, in the guest physical, then that may not necessarily trigger this appropriately. That is, I think, something where from the software point of view, it may be necessary to like distinguish this better. Like PCIe has, for example, ATS support, and for example,
well, yeah, but that is the second part is about IOMU. Okay, with IOMU, the spec says you will need to work with ATS.
Yes.
Okay, and I don't think ATS is enough for ensuring security in virtualization. So if you at the end are going to allow a CXL device pass through to a VM, and it's going to use CXL cache, ATS is not going to work. It's not enough.
You have to trust it, but this is standard trusted device flows if you're using ATS. There's no different from PCI. And you have to use an IMMU and ATS. I mean, I don't think anything sane can happen without that for a CXL device. And the spec is written with the intent that that's what you're using. There is no direct physical address stuff.
My question was, I hear a lot about device pass-through for virtualization. I always kind of question whether or not full pass-through makes complete sense rather than having a slim virtual device that abstracts it away.
But what the problem is, if you give a CXL device to a VM,
yeah,
which addresses are going to be used by that device?
Right, but this is a configuration path piece, right? So you don't want to pass the commands directly through to the device. You want the host to set something up. Well, I guess it depends on what your hypervisor setup is, but in my head, you have the host set up virtualized regions, and then you pass that to a virtualized CXL device for the configuration path.
There are two things here: CXL mem and CXL cache.
Right.
Okay. With CXL mem, there are ways to solve that problem. You can do that before the VM is started, or you can do you can have a VM exit and do that when someone inside the device inside that VM wants to do that. But with CXL cache, the problem is going to be used. The device is going to use DMA addresses like another kind of pass-through device, but or you have IOMU, or that device cannot be safely given to a VM. And the point is, if you have ATS is not enough in that case, and you need to go with IOMU. Okay, if you read the specs, it says with IOMU, well, that you need to use IOMU with CXL cars. My point is, if you have to use CXL cars with IOMU, what's the point of having CXL cars?
Exactly.
But no, with ATS is using the IOMU, but with ATS, the packets are the TLP packets from PCI are just going through the IOMU hardware without any check. Okay. Yeah, but the point is with CXL cars, you cannot have that, or the point of CXL cars, in my opinion, it doesn't make sense.
But I think there's two aspects. Like ATS, as it's defined for PCIe, is not necessarily covering CXL pretty well, acknowledged. So that is again something that can be improved. I think the main problem that I think you're dealing with is two aspects. One is the invalidation of the TLB caches and the technology of the endpoint caches that are on the device that may either store the guest physical or the system physical, depending on what they're seeing, right? Typically on PCIe, you go with the system physical, right? So that if your cache is not tagged with that, then you may have problems if a transition is happening. But you will have to validate everything, or you have this mechanism. If you go with a guest physical address, for example, you may not have that information. That may be a problem then for the device itself to keep its particular content.
Yeah. So all this is from my concern is, okay, if there's a way where you can allocate CXL cache addresses for a device safely from the host, and then that will not require IOMU getting involved for safety, okay? So at the end, it depends on the host allocating specific addresses. Then we need to know that, and we need to implement that in the kernel. And then we need to rely on the driver doing the right thing with that API and not whatever they want. At the end, we need to trust the driver, whatever. But we need, if that's the case, we need to modify the IOMU and to get involved if other people from the kernel, IOMU guys, of course, to get clarification from how this is going to be implemented. My point is for passing through, a device cannot use CXL cars right now.
Why? I actually am not understanding what you're saying. So what is the problem with CXL.cache in a VM? If it's a hardware implementation of ATS, right, and there are time of use checks in the IMMU, what does this say? I don't see any problem. What is this security problem you're saying? Why is it not trusted?
Problem typically is on the PCIe definition. Sorry, the microphone. Okay, didn't know that. Anyway, for ATS, as it's defined for PCIe, there's for example the ATS transaction where they request the translation from the guest physical to the system physical in the device itself, right? I mean, we will give it back, and then there will be a trusted transaction back to the host complex in order to actually do the system physical access, right? And that is essentially, if you have some device that can spoof that, then that may be a potential security hole. This is what's fixed right to CAS.
A VM is a user space, and user space is not trusted. So you cannot allow the user space do whatever. Yeah. No, but the provider needs to do something about it.
It's standard two-stage translation. The guest is doing the
ATS
GPA.
with IOMU implies you can get the DMA addresses from IOMU through this protocol, okay? But you need to ensure the one that is working with the device that is inside the VM is going to do the right thing.
That is the hardware, right? And you can do attestation of the device.
Yeah. Yeah.
Okay.
Okay. No. This is all. I mean, okay.
Yeah, I'm not seeing any problem. Like if a system architecture has, time of use checks, you can use device attestation. It's hardware-backed ATS. There's no problem.
Yeah, no, I agree. And to your point about if you have to get the IOMMU involved in the translation, then why are you doing .cache anyways? You've already lost any benefit. But you have to get a system address in order for the device to do anything useful, because the device at that point is sending stuff directly to a cache home agent, right? It's taking a line out of the cache home agent for the coherency protocol, and it's not going to go through the IOMMU. It's going to get a time of use check to make sure it's a valid address that you can use. After that, it's like endpoint to CHA, and that's it, right? There's nothing else in between. If you stick something in the kernel in between it, you're destroying the performance of that.
Yeah, I agree.
So I guess I don't know what exactly it is that we need to build.
Well, a safe way of doing CXL cache from inside a VM. A VM is not trusted; it's user space. So if you give that VM a device that can do DMA, and it can put any physical address for doing DMAs. No, that is not how it works. No, it doesn't work. You can allocate without any action from the hypervisor from inside the VM. They may, yeah, you can give whatever you want. Yeah. No.
So I want to add one comment which was mentioned about the device attestation and the hardware attestation specifically, which was mentioned. So hardware attestation itself is very costly. If you really do hardware attestation, that's going down to the EL3 level, let's say for ARM CCA, that's really, really expensive. So people sell it badly, but they don't actually go down to that level of hardware. It's only done, for example, for Intel TDX, Intel SGX, it's done only by quoting enclave, which is not hardware. That's a software, that's piece of software. So it's not going down the level to the hardware. Even for ARM CCA, it's not going to the platform attester at all. It's only being signed by RMM. So it's sold as being hardware attestation. It's not hardware attestation at all. It can be hardware backed, but that is really, really costly. So each attestation, if it goes down to the level of the hardware, that means every time you call these functions, it's not done once. You could have runtime measurements which are changing all that, which may change. Like it depends on your use case, but it may change. Sorry. So if your use case requires that one time, sure, that's fine. But if your use case requires runtime measurements for RTMRs in Intel TDX or in CCA, I don't know what they call it. I forgot the name. But if you need it repeatedly, then it goes down to the hardware level. That's really, really costly. And nobody, including ARM, Intel, AMD, nobody is doing it at the hardware level, really.
Yeah. May I ask one last comment? Yeah. So in virtualization, the VM, the hypervisor will create the IOME mapping for that VM. And inside the VM, you think you work with physical addresses, but you really work with IOVAs. Okay. So when the device get this IOVA for that DMA, that goes through IOMU. Okay. But the driver or whoever is inside the VM can put whatever DMA address he wants for doing the DMA address operation. And that's the reason for IOMU. So if you don't have IOMU because CXL cache is going through another path, how are you going to be sure that the DMA address is the right one?
I don't know.
I'm calling time.
Yeah.
We're doing Rajneesh next talk.
Okay.
Yeah, because anything we go over, I'll have to steal from lunch. You guys don't want me to steal from lunch, so thank you.
Okay, you're here.
All right. You guys can hear me okay? Yeah. So good afternoon, everyone. My name is Rajneesh. I work for AMD in Data Center GPU division, and I work on AMD Instinct GPU system and software architecture. I have with me Senior Fellow System Software and Firmware, Paul Blinzer, who will be co-presenting with me this talk today about memory management challenges for machine learning, AI, and HPC workloads. So I think our aim for today is to basically describe the problem that we realized a while ago, a couple of years ago, when a customer reported that our GPU driver does not load, it simply crashes. And the crash was coming from a place where we were not expecting it from. Upon some investigation, we found out that the driver is trying to do an IO remap on certain memory ranges, and it is not allowed. So there was a bug. And we sort of, for the time, we realized that the problem is that some other component or entity in the system is claiming the GPU resources already. For that time, we had a workaround. We booted the system with EFI no reserve, and we loaded the driver back again so that we could continue. And we started looking into this problem from a deeper understanding perspective, and we realized that this is basically a bigger space where we need attention from from Linux community in general, especially for the heterogeneous system architecture and the evolving system architecture for the current generation, because the problem cannot be viewed in isolation, primarily not only focusing on it's a GPU problem. So the agenda or the aim for today will be to discuss the problem, and then we will propose some potential workarounds that we think are plausible solution, and then we'll go from there. Some background first. I think the main heterogeneous systems that exist today on GPU, involving GPUs, are typically the PCI connected discrete GPUs, which have a dedicated, vendor provided GPU driver, completely manages the memory management and everything that has to do with the GPU. Then we have something called an APU, which is HPC programmers, dream, where CPU and GPU dies are on the same silicon. And in some cases, like MI300A Instinct APU, we even have HBM on the same silicon die. So basically, what that means is, on such a system, CPU, GPU, and HBM are on the same physical space. That means when Linux boot on such systems, it boots out of HBM directly, thinking it is a system memory. And when the GPU driver loads, we fake it. We tell that, hey, you don't have any VRAM to work with. You have 0 VRAM. Then GPU driver says, hey, how am I going to work? So we say, you piggyback on TTM layer, piggyback to Linux's core memory management, and you deal with it. Like if you need a VRAM allocation, go ask Linux. Don't allocate it, and fake it. Like if an application is trying to allocate VRAM, you acknowledge that, you give them the virtual address back, but the backing pages are coming from Linux core MM through TTM layer. So that is there's a second level of hybrid heterogeneous system architecture. And finally, the problem in this one is that the CPU cores may not be as strong as today's machine learning and HPC workloads demand. So we have another heterogeneous system architecture, which is called A+A. We have an AMD CPU connected to AMD GPUs, and it is a full server class CPU, like Rome class or Venice class CPU connected to data center strong GPUs like MI300X or MI450, and they are connected through Infinity Fabric. It's a hardware coherent interconnect, also known as XGMI, ultra low latency, high bandwidth interface, and it provides HBM cacheability to the CPU in a truly hardware coherent way. So this is basically the third type of architecture, heterogeneous system architecture. And in such architectures, we still have the GPU driver managing the GPU, and it treats the GPU memory as part of the extended system memory map. Now, another approach that is coming into force these days is the driver managed RAM approach, which is popularized, I think, by Grace Hopper, Grace Blackwell, NVIDIA architecture, where they hot plug HBM into system memory, and they use CXL style mechanism to hot plug GPU memory ranges and provide the numinous for HPC applications, and still make sure that this is a privileged region. OS should not be providing any general purpose allocations in that space. It should still be specifically used for specific driver managed allocation for the GPU memory. But finally, what we have at AMD, or what we intend to use, is the specific purpose memory, which is basically the theme of this micro conference. So SPM was, it's not new. It was something that's existed for a long time. And the idea of SPM was then that the platform firmware, the UEFI aware firmware, will declare the memory in the platform definition as EFI memory SP. And then what happens is when Linux boots, the EFI subsystem looks for the memory map provided by the get memory map system call, and based on that memory map, it parses and it sees this SP flag, and if that is also ORed with write back attributes, then Linux treats it differently. It marks the E820 structures, and it sets the memory type to soft reserve descriptor. And what it means is then once DAX subsystem loads, once that Intel DAX driver loads, it sees this is a preferred type for its attachment, and it claims the SPM regions. So this is pretty much the summary of what SPM is and what's happening today. How it impacts us is described in this picture. As you can see, we have AMD Instinct GPU, and in the middle is a system address map, and there could be more than one GPU, and each GPU will have its own memory ranges described by the specific purpose memory range defined in the platform BIOS. Our expectation is that this should be claimed by AMD GPU driver, which is the primary authority or the rightful owner of this range. But what is happening today is because of some earlier design choices. I'm not saying they were wrong; they were appropriate for that time, but it is conflicting directly in today's world, real world. We are having this real problem. So we are having problems when our customers are not able to use DAX subsystem in a rightful way with our GPU driver, and using something like DAX control is cumbersome, especially for cloud service providers. They cannot offer to tenants, right? So this is where we stand out of today. This is the problem space, and I will now hand it over to Paul to discuss some of the options that we are proposing. Paul, take it over.
I think I rather want this on. There you go. Better? Wonderful. So my name is Paul Blinzer. I'm working at AMD, as you may have guessed. And so the thing is, like Rajneesh already described the problem that at hand. Again, there's always history to everything. Well, okay, the question is, okay, what do we do with that? From my point of view, and I think you may agree, the SPM mechanism as a mechanism to expose memory is the preferred way from the platform point of view, because you can actually define the regions from a platform, and operating system picks up, can understand all the properties from it, from UEFI, and then go forward. Now, I understand, like, for example, you can also do hot plug memory, but what you want to achieve, or what SPM is doing versus the Java-based approach, is making sure that the operating system does not claim memory for generic allocations, but really reserves it for the components that can actually make best use out of it, right? So, and yes, hot plug memory works, but this, like, it prevents the operating system from using this in a general way for the wrong reasons, right? Because again, hot plug means that the memory can go away, and so all the content can go away. Whereas the use case that you have here is that memory is actually like locked down on the system, so you cannot really remove it. But so it's not movable. And but you still want to make sure that your operating system understands, okay, this is something that is used for the application space, etc. And the main problem here is also that there's no API in the kernel to actually reserve, no, this is not your memory for the DAX. It's something that we need to use, and we have to manage, for example, the page sizes. We need to make other page management policies that are not necessarily the same as the regular operating system driver, operating system manager would do. So, so there's multiple options that what can be done there. So well, we've thought about this quite a lot of what we can do in order to fix that, and we had like a lot of discussions with the DAX maintainers. And like one of the items that I see in terms of like the architectural way of doing things, and I'm looking also for like input from the community here, is like utilizing an ACPI device that owns the ranges that it's actually managing, which is device for the platform. Operating system in early boot finds out which are reserved, and anything that is not necessarily managed in like specifically with a particular driver, which is associated with an ACPI-based device definition, would be then owned by the DAX component itself. So this way, what this means is that from the point of view of the platform, you can use pretty much the regular ACPI mechanisms for SRAT and HMAT, etc., to describe your platform, like bandwidth, latency, and NUMA topology just fine. So that all works. The RAS mechanisms that are also defined through ACPI structures are also like rooted back in the actual firmware definitions. So you don't have this codependency between a driver patching up certain components in the main kernel. And you can then pretty much utilize those particular tables also and validate it. For example, if you have like secure environments where you need to make sure that whatever the platform is reporting in terms of resources are actually platform resources that are relevant, right? Like with DRTM or other things, other mechanisms are standardized.
Next one, Paul.
Yes, please. So again, some of these mechanisms are already used, for example, for CXL memory to some degree. So the option that we have, that are variants of, that we have thought about, is having an interface to the DAX stack that will allow a kernel module to say, okay, this region is actually something that we want to manage and then take over. This would be pretty much working the same way. So an API driver would, different definition, would load a driver that then has an interface to the DAX stack to reserve the particular range for itself. But that would also like introduce some codependencies between components, and it's also could be a little bit hard to scale in some ways. The other option, the third option that we have thought about, is that using like what has been defined for CXL, like there's CDAT for what is coherent device accelerator coherent
attribute table.
Yes. So, but there's a table that is like pretty much consumed by the firmware and or by the operating system to understand the coherency properties, etc., and has a description. And this is typically attached to a discrete accelerator to define those particular properties that extend what PCIe reports in the config space and what is the operating system needs to know and to understand cacheability and other things.
Yeah.
Problem with that is the underlying infrastructure, like the data fabric we're using, what we call Infinity Fabric, is not CXL, and there are some like codependencies. Like if you assume that you have if you have a CDAT, it's a CXL device, may not necessarily work all the time. So that is not necessarily a stable solution from our point of view. Yeah. Next one. So ultimately, it boils down to two things. We can always do something in the new kernel, right? The problem is, what do we do with the old stuff? And again, there's a lot of reason why open source is great in terms of like changing something, but sometimes like you don't want to change the kernel. You want to use whatever you have, but you want to enable certain things on it. So the problem with it is, how can a platform, for example, avoid that the DAX stack is loaded on a legacy kernel? And then one way would be, in terms of like what can be done there is, well, you either block DAX completely by a boot option. Well, this works, and this is currently, I think, the option that we recommend for people that are utilizing this mechanism. Yeah. But it's also not really satisfying. The other options would be to like have some way of defining a mechanism that DAX is reserving this memory for other purposes, and then let the driver take over. At the moment, the DAX is pretty much one of the first components that owns the memory, and so getting it back again to a driver use is the problem here that we want to solve.
Yeah, so basically pretty much what we're trying to ask in this forum is that there has to be a way to find the association of the SPM ranges with the, so basically make specific memory actually specific, not a generic memory claimed by DAX regardless of the intended use of that memory.
So I keep getting stuck on why is it SPM? Because especially if we have an ACPI device, if the ACPI device and then with ACPI we can describe whatever it wants. It can describe whatever resources that the device needs. If those resources are reserved,
yes,
then DAX will definitely won't touch it. Nobody will touch it, and your ACPI driver will load and use it, and off you go.
Yeah, I mean that's one of the proposal, right? Like that's not the situation today. So is that expected an agreeable approach to go forward?
No, I think it's no. I mean, yeah, I think because SPM is conventional and it is conventional memory, and if you have an OS that doesn't care about the special purposes of it, specific purposes of it, then it can treat it as conventional.
Yeah, but that's the thing. Like if you do an EFI reserved on that range, for example, right? Then what you tell the operating system, don't use it at all, right? If you have for example, some cases where you don't need,
driver can take
the driver can use it. But
driver can use it.
It's driver memory then.
Yeah. So basically, like the ACPI device would declare a bunch of reserved resources, and off you go.
The eventual goal here is some combination of having the driver produce what would otherwise look like system RAM in a NUMA node?
Exactly.
Okay.
So essentially,
yeah, but
making sure I understood.
From the operating system point of view, this looks like any other memory. It's only special in the way that it has better bandwidth, and you want to use it for a particular purpose for the application space, so that it knows it's pretty much a separate pools of some kind. But otherwise, you can, if you don't care about this particular aspect, you can just let it all go to the memory, the memory manager of the operating system, and use it as just stinking old RAM.
Yeah. So there's two problems, right? There's the configuration piece, which is we'll call the plumbing issue of DAX taking the memory, and then you have to deal with that whole integration.
Yes.
Then there's the allocator piece of like, how do I prevent the allocator?
Let me just clarify one more small point before you go there.
Yeah, go ahead.
So basically, the expectation is that for the operating system, this memory region should be forbidden for general OS core data structure allocation. It should not be touched. This should be like it may appear like system RAM, but it is not actually intended for using like a system RAM. It is supposed to be used for a very specific purpose, which is the accelerators, core kernel shaders.
I'm not arguing any of that. Yeah.
Okay, so that's that. Now, having said that, what we want is that the current usage model is ideally we want a valid CPU pointer to be a valid GPU pointer. So let's say if someone does a malloc, and if GPU touches that malloc virtual address, and GPU takes a page fault, and then HMM and shared virtual memory, Linux HMM triggers, they move the SVM ranges, they move from one domain to the other domain. This is typically how it is supposed to use. So CPU can still use the allocations on HBM and vice versa, but it doesn't mean that OS is free to use for
Right. I'm just pointing out that there's two things you're talking about here. There is how do you make the kernel understand what the configuration is.
Yeah.
And then there is the how do you prevent the kernel from using it as general system RAM, which is a separate discussion.
So as long as the SPM remains specific, kernel won't touch it. But right now,
sort of, if you online it like I don't want to touch that piece right now because I'll talk to you guys later
we can
length with that.
For sure.
The first piece, I think what Dan's getting at is the CXL driver does this with
mailbox
ACPI tables, with the ACPI descriptions, CXL driver is given a chance to claim the memory before DAX claims it.
Yes.
Right.
And I guess what you're saying here is that you can do that for new kernels.
Yes.
How do we deal with our old kernels?
Yeah. Yes.
And I don't.
And even then, I think again, what I was like highlighting, the CDAT mechanism, for example, is there as but it's also like something where it might not necessarily CXL. Like there's certain properties of what CDAT assumes in terms of like the hardware properties that may or may not necessarily apply to the configuration that you have on the hardware side. So the point is that the generic mechanism that CDAT is doing is great. But the thing is, it should be generalized in a way that it allows, for example, other ACPI components, or ACPI-defined components, to claim those resources.
Maybe my mental map is wrong, but I don't know that has to do with CDAT in particular.
And not with, there's like this mailbox mechanism like again, CDAT was defined essentially for the firmware and the operating system to patch up effectively what is the understanding of the system based on the information in the table itself, right? And that assumes certain communication mechanism between the firmware and the operating system and the hardware that are not necessarily available on the platforms we're talking about.
Yeah, so like what's the like general recommendation? Like we presented a few options. So what do you guys think is the right way to go forward and do some implementation?
Let's huddle, but I want to understand the constraints on whether, like, if you can just do a firmware update to say this is reserved and not SPM, and if you can deploy a driver update to your customers.
For the legacy systems.
Yes, just two aspects here.
For legacy.
The main problem is like, the thing is there's application scenarios where you want to use this as accelerator memory only, right? But the thing is that if you don't have an application scenario, for example, where you want to use the platform, not necessarily with accelerator, but for general purpose use, then you can still, with the approach of having SPM, you can still use it as ordinary memory and essentially get performance benefits from the additional memory that has been provided instead of, and that is essentially a benefit versus the other thing, and this is also applying to legacy kernels still. Whereas if you have like a reserved range and use a driver, then you automatically take it out of the regular operating system management, but it's also not available for the definition. Thanks for.
Okay, thank you everyone. Unless there is a question, maybe.
Oh,
are we allowed?
Short.
I also have a question too. Okay, yeah, thanks for the session here. So I think we also discussed about like why SPM there, because like we want to add a special device memory and we don't want to mix it with some host memory side. We do have actually like from our workload there, we do see this kind of issue. And but my question is here, like, so for the SPM, why you set it to SPM? Like if you driver management side, you can isolate this memory.
Yes.
And it's by yourself. Like you know the CDMM, right?
And of course, no, but again, if you have a driver-based approach, then there's like multiple aspects to it. One is security. The hypervisor and the guest has to trust the third-party driver in some way. And well, for open source, this might be not, you can audit it. It may not necessarily be always available based on the system that things are running on. And it's also something where the driver may not necessarily has a codependency. So you have essentially platform OS and OS kernel and driver being codependent on each other to report proper things. And this this codependency is problematic and fragile.
But doesn't the driver manage it? Why the? I just don't understand why the.
I think this we can take it to the huddle room.
My point's just really quick on the having all that memory and having it online when you're not using the accelerator. I wouldn't optimize that too much. I mean, we found that people have spent all this money on fast memory attached to an accelerator. They want to use it for an accelerator, so I wouldn't worry too much about that.
Yeah, but the HPC workloads. Yeah, I think. Thank you, everyone.
Can you hear me? Okay. Okay, let me start. So thank you for joining this. And my name is SJ. I'm working for Crusoe and maintaining Daemon. So I want to give a background about the NUMA and Daemon, and then discuss about Daemon, utilizing Daemon for memory tiering and more holistic NUMA migration, and have a discussion. So first of all, let me just recall my dumb understanding of NUMA. That is, the NUMA is a kind of the access or memory system that having access speed that depends on some multiple factors, like what is the accessor and what is the accessing memory address. And Daemon in 1 minute is that Daemon is a Linux kernel subsystem that designed for efficient data access monitoring and doing access-aware system operations. And it allows the users to know the location and the recency and frequency and stability of the access, where the access was made, how frequently the access is being made, how stable the access frequency is. In other words, what is the recency? And there is a feature called Deimos, which is automating the data access over operations, like finding pages that not accessed at all for 2 or more minutes, and then reclaim those proactively as soon as found. And therefore, there was some people who finding that Daemon might be able to be used for memory tiering. The first people were people from SK Hynix. They have implemented a very simple capacity expansion on CXL and DRAM memory configured systems by utilizing Deimos to migrate hot pages from CXL to DRAM and migrating cold pages from DRAM to CXL. In other words, promotion and demotion. And how the hot and cold threshold is made, that is tuned for their use case. And it has been released as the SK Hynix HMSDK, and according to recent presentation from them, it was showing up to 94% Lambda CPP benchmark speedup. And secondly, when I was working for Meta, I have had a chance to access to some CXL memory configured systems, and I implemented the Daemon-based TPP IDE implementation. TPP is on a paper that published in ASPLOS, and the idea is very simple. It is just put as many hot data as possible in upper tier, as long as it has the headroom. And the implementation is to do auto-tuning of the hot and cold threshold for promotion and demotion to achieve the TPP goal. And it was showing about 4.42% tau bench score increase. Tau bench is another benchmark representing some in-memory cache. Yep. And recently, Micron has also started working on utilizing Daemon for better optimizing their CXL systems by using a kind of dynamic interleaving, and it was showing about up to 25% benchmark speedup. And there are some more work in progress that going on publicly and privately. And let me explain TPP implementation in Daemon in more detail. So the idea is very simple, but also scalable, because it is just promoting the hot pages to the upper node as much as the upper node, which is valuable, can more utilize, and demote cold pages only for keeping the headroom. That means that it can be applied to n tiers. And this is the more detailed implementation of TPP Daemon. Please bear in mind with me. There is so many text, but what it is saying is that, dear Daemon, start Daemon in kernel and monitor the node 0 and do some kind of magic auto-tuning and migrate unaccessed memory on the node 0 to node 1, call this one first, but do it only once per second, and within 1 second do the demotion only up to 200 megabytes of memory so that you don't consume too much resource of the system for only demotion. And also do that aiming 0.5% of free memory on the upper tier, upper node. And of course, because Daemon can be done, please don't do the migration if the page is young. And very same thing for promotion. And how it can be extended for holistic NUMA management. The idea is very simple. So actually memory tiering is only a special case of NUMA system, right? Just having 2 NUMA nodes or n NUMA nodes that attach to all CPU. And therefore, it means that it is just a kind of NUMA topology that having single promotion and demotion paths. And therefore, general NUMA would be just having n accessors like CPUs, GPUs, and any kind of processing unit. And therefore, the idea is there could be n promotion demotion paths, and let's implement TPP instance for each of the paths. Like this. If we have the 2 accessors, namely CPU1 and CPU2, then we can have TPP1 instance doing the migration of the CPU hot cold memory from DRAM1 to CXL.mem1, blah, blah, blah. And can Daemon do that? Right now, no, Daemon cannot do that. daemon of today cannot do that for a reason, but it is willing to do that in future, and how we can do that. Before saying that, why daemon cannot do that? Because, before again answering that, we have to understand how daemon is implemented in each layer systems. Daemon has two layers. One is core. The core is doing some kind of magical, not that magical, but some dumb, but adaptive mechanism for finding what pages to check access for, kind of sampling, and then assemble the sampled access information to some upper layer access pattern picture. And there is down layer called ops. It is for dealing with the hardware specific primitives like page table access bit. It checks if the core specified samples are accessed or not, and then just pumping the information up to the core layer so that they can make some good picture with that. And the current existing daemon ops implementations are VADDR and PADDR. That's because they are different layers. You can implement any kind of your operation set implementation in ops layer and then connect that with the core. And currently we have VADDR and PADDR for virtual address space and physical address space, and both are using page table access speech. That means that because that's only access speech, that lacks the information about what was the accessor. And how can we make it? It is just simply you can implement new ops implementation for your preferred hardware primitives like page fault event or AMD IBS like instruction sampling or CXL HMU, and then pump the information to core.
One quick question. You know, like with the AMD presentation about getting unifying the sources, it's the same thing in some ways, right? Like if we exposed what they had to user space, would it be doing the same thing? Like, well, do you see a relation to their work?
Yes, I show some kind of similar and common parts. Maybe. Yes, I show some similar parts.
I mean, would you basically be a client of PG Hot? So like PG Hot could be collected, and then PG Hot feeds daemon.
John, when we were discussing both daemon and the original form of work, I proposed to split out K-migrate-D for exactly this purpose. So page hop might be one form of tracking the data. Daemon might be another form of tracking the data. They both might use K-migrate-D, and then we could generalize the solutions, right? So, but daemon had already gotten quite a bit of way forward. So, yeah, similar ideas though, right?
Yep. So that's one example case that we can make it, but whether it is really streamable, upstreamable, probably not, because the making a new orb is good for proof of conference, making a fast proof of conference, but in terms of the maintenance, there could be too many ops implementations that having duplications, and therefore we are working on a streamable approach that is called daemon report access. This is a new kernel API that provided by daemon that letting any kernel component be able to report access to daemon. Yes, I showed the commonality with the PG Hot. You know, there could be some similar things. We are all humans. And then we are working on making a facility in daemon for fine tuning and controlling of the sampled access information by kind of letting API and ABI to be able to specify daemon what primitives the user or caller really want to use with current daemon instance, and what kind of filtering of the reported information based on the additional information they want. Like, okay, I want to use only page fault event, and I want to ignore any access information that was made by CPU 1 or CPU 2 or CX or GPU or etc. In that way, we can do post CPU monitoring, post thread monitoring, for read-write only monitoring. So the progress is that the RFC third version has posted a few days ago, and at least you can check the implementation proof of proof of concept level implementation, it is very poor and unoptimable at the moment, but at least you can get more idea about what dumb idea I'm saying about. So we want to further work on making it off-streamed, not only for NUMA, but also for some other use cases. For example, AWS was showing interest in using this for write-only monitoring to find better live migration candidate of the virtual machines. And there are some challenges, especially for conflict with NUMA balancing. I want to further discuss with NUMA balancing people and also core maintainers, because it will add some hacks on there. I want to make it as clean as possible and not distracting others.
It wasn't to point out the similarities. It was that maybe you can work together to do this, right? Like, I think it's close of what you're trying to get done. Like, Damon maybe is a consumer of the same information.
And it's worth pointing out that Damon has a pretty rich user interface and visualization environment already. And I think the question is, if you talk with the hot page working memory group, you might be able to, well, I can see why it would be difficult. The policies he describes here are way much further along than what PG Hot can do right now. But I guess my question was, we saw there was a memory overhead of 0.2 or 0.5% from the 0.2%. What is it? Have you profiled what the memory overhead for the, what is it, Damon report record is? Like, have you designed that yet?
Actually, that's inside the design of Damon, and the in short, the answer is that the memory overhead of Damon can be set by users regardless of the size of the memory, because the memory overhead is proportional to the number of something called Damon regions, and users can set the upper limit of the number of the regions. The 1,000 is the default, and therefore the approximate memory overhead in default setup would be 1,000 data structures, so about 64K, regardless of the size of the memory of the system. So on 1 terabyte memory system, 1 exabyte memory system, the memory overhead of Damon should be same.
Yeah, so a few questions basically, especially related to the comparison with the PG Hot subsystem, right? So in the PG Hot subsystem, we are tracking every single PFN hotness, right? How does that compare with the Damon report or Damon record API that you have? And when he asked about the memory overhead, right? You are saying that you track the hotness in the form of regions, where PG Hot tracks in the form of PFNs or per page. That is the overhead per page. So how does that compare actually?
Compare of overhead or accuracy?
With the region-based approach.
In terms of accuracy or overhead?
In terms of the space overhead.
In terms of space overhead. In terms of space overhead, as I just mentioned, Damon just keeps the upper limit of the memory overhead as user want, regardless of the memory size. In other words, if user really want to do page granularity monitoring, then users should specify that they want to set the number of regions as number of pages. And in that case, the memory overhead would be even much larger than that of PG Hot, because Damon region data structure is about 64 size, if I remember correctly.
Yeah, one of the base where we started the PG Hot work is kind of try to get where existing hot page promotion is, which works at per page granularity. So I was interested in knowing how would that compare with the region-based approach that Damon has.
That makes sense. That is, Damon is not designed only for page granularity monitoring, and therefore there could be difference, especially in terms of the accuracy. Nevertheless, I would say, so actually there was this kind of question about whether Damon can do page granularity monitoring from the very beginning of the days. And the answer is that if you want that, then you can just set the number of maximum number of regions as the number of pages on the system. Of course, it will make the overhead much larger. And also, if you want to further optimize that overhead, then again, you can implement yet another ops that having such kind of things, kind of optimizations. And actually, I implemented that on my own when Daemon was not upstreamed yet, when in RFC stage. However, we found no real use case of that, and therefore we didn't upstream that, and we didn't revisit that yet. But if there is any need, of course we can do that, and I'm always open to work together with PG Hot.
I think what I just learned off of this is that there might be a scenario where, PG Hot does the page level tracking. And then if you want to do further complex region level tracking, because it's more memory intensive, and Daemon, you can do that. And so you can do that even at the virtual address space in Daemon and get more complex. So I think there's, real value in potentially having Daemon consume PG Hot data. And then maybe deferring migration decisions from PG Hot to Daemon, or maybe even the other way around, right? So I think there's value in that.
That makes sense. I believe that PG Hot and Daemon can also work together in such a way. Yeah.
Yeah. Other thing I was wondering about is, the objective I had in mind for PG Hot was just report the accesses and let everything be handled automatically by the subsystem. But I see that Daemon requires all these policies to be set externally, right? That's the difference, I guess.
Yes, the policy should be set by users at the moment. Nevertheless, I'm also trying to, I may work on making some decent default policies that can be turned on in much simpler way than the multi-lines of the command line. But yes. Do we have some more time?
Anyone?
Okay, I think that's it, right? So thank you very much.
Okay. Hey everyone, is it working? Is it work? Okay. 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 So welcome to this session. So first of all, about this protected DMA buffs. So these are very new to the kernel, first of all, just to be clear. But the use case here for protected DMA buffs is pretty old. Like we all play secure media content or the media streaming from Netflix or Amazon Prime or whatnot on our phones. And that use case has been there for more than a decade. And all the implementation for that has remained downstream for the kernel. And many different ways have been tried to support the upstream use cases. But now we have found a way to make it much more generic. So let me first come on to the use case. Before going there, first of all, who I am. So I'm a member of the Qualcomm open source team. And I have a keen interest in open source boot and security, from kernel, T subsystem, to all the boot firmware stages, EDK2, TFA, OPTI, and maintaining bits and pieces here and there. And in U-boot, on the device tree stuff. So yeah, I'm all about that. But you can see it's all centered around boot and security. And so that's my core area of interest. Now, to describe the secure media pipeline use case, this is an abstract view how it works. But normally what I've shown here in the user space as a GStreamer media pipeline, because that's the open implementation of any media pipeline. But usually what the downstream that Netflix or others use, there are Widevine solutions, there is Microsoft PlayReady. Those are the user space components. But from an open source point of view, we are trying to make a solution with the GStreamer pipeline. And here you can see the components here. Normally, a media pipeline on an unencrypted media stream that works via the system heap. So mostly all the allocations for your normal media pipeline, when you're playing some content on your phone that is unencrypted, that is going via the system heap, and all allocations are from there. And how the media pipeline is constructed, that is usually the decoder comes first and then the display engine, and that's the minimal pipeline you would like to see. However, with the encrypted content, there comes the decryption engine in between as well. That is usually a crypto engine or the hardware crypto engine that is being used because of the security. So here the main motivation is, or the main use case is, like the media content shouldn't be accessible to the kernel or the user space in the plain format. So it should always be in encrypted format, and only the pipeline, the device pipeline, that is able to access the content in the plain format, not the kernel or not the user space. So that's where this protected DMA buffs come into picture. And here, what we have come up with via the T subsystem. So first of all, let me describe the T subsystem as well, because there might be confusion that confidential computing would also call it a trusted execution environment for the confidential payloads. And here in the ARM Trustzone world, or RISC-V Ts, or the mobile world, we call trusted execution environment that is a piece of software that is very minimal, running on the secure side of the CPU. Basically, what we call it as the secure world. That is the minimum TCB which any vendor can trust, and which is auditable and certified by the by the uh, by the vendor, basically the end OEM that is certified, so that uh, that piece of software is able to access this secure media content in the plain format as well. So the CPU has two modes of operation. One is the rich world of operation, that is the Linux side, and one is the trusted OS that is running, that is very minimal, and it is something that is trusted. That's what we call it. So here you see the T subsystem here is mostly trying to abstract out details about all the hardware implementations of the trusted OSs that are there. So global platform is one standard body that is trying to standardize the communication with the trusted OS and all the trusted applications that are running over there. So here, so why the subsystem here? Because every silicon vendor has their own way of establishing memory firewalls. So usually there is an IP block on a SoC that is sitting in front of the DRAM that is enforcing memory protections based on the CPU mode or on the device access side as well. So different vendors have their own implementations, like NXP, Qualcomm, MediaTek. Everybody has their own way to set up the firewalls. And that's where the T subsystem is providing the abstraction for the memory firewalls to be set up for the buffers. And yeah, so in this case, the content, the encrypted content would be there in the system heap. And the first first device in the pipeline would be the crypto engine that would decrypt that content into the protected DMA buffer. And after that, plain content in the protected DMA buffer would get passed on to the hardware decoder as well as the display engine. And in this pipeline, the software is not able to access the content at all. So as I've described already, so the effort has been going for many years, and the mainline kernel, we didn't had a use case in the mainline kernel. There were some limitations that were there because there wasn't an end-to-end use case in the open. Basically, that was the main obstacle, like for the kernel mainline to adopt the kernel interfaces, I would say. So the kernel interfaces were being proposed, but not the end-to-end open source use case. That was all these Widevine or Microsoft Play Ready implementation. They're all like they're not open. They are just downstream and proprietary. And so that's why we are trying to come up with a GStreamer based solution that can be an open stack that is that anybody can exercise in the open with Opti. And Opti is one trusted OS implementation that is open source. And here you can see all the things that run on the trusted side of the core is also open, and people can view all the end-to-end use cases for the secure media pipeline. And the second difficulty was the vendor-specific metadata. So many earlier attempts at the kernel was like people came up with these DME heaps that were vendor-specific because of the memory firewalls. Whatever has to be implemented, they were vendor-specific. And so there were like many different DME heaps being proposed, like from MediaTek or from NXP. So yeah, that wasn't going to scale because DME heaps doesn't allow to plug in the metadata like for every vendor. So the T subsystem came into rescue to enable that metadata to be stored within the T subsystem, and it would be the exporter of the DMA bus that would be consumed by the other subsystems. So there are two ways to implement protected DMA buffers. So one is the static carve-out. So say, for example, the memory firewall is just set up by the platform during the boot stage, and it's just the reserved memory regions and which are just consumed by the kernel, by the devices. So allocation happens from there, and it's just like a reserved piece of memory that kernel can't reuse. But especially on this mobile devices or the embedded devices or whatever you see in your car, they are resource constrained. Like the DRAM is very limited. So yeah, this carve-out solution could work on there, but when there is like hundreds of megabytes of allocations for this for the secure media pipeline, then we are really reaching the limits of the DRAM. So that's why an efficient reuse of memory is needed. So we can't work with these reserve carve-outs for like very memory constrained devices. So yeah, that's the backdrop of this static memory carve-outs. Although it just works, so kernel doesn't have access to the memory at all. But yeah. Even the support of scatter-gather allocation, where the pages can be scattered all across the memory, and for efficient memory reuse, this approach just limits us to the shortcomings. Now, the second point is about for protected DMA buffs is the dynamic memory assignment. This is like we can allocate pages from anywhere which are free in the memory. So similar to the way that system heap works. So you can allocate pages all over the memory range, and you can map it into the DMA address range for the device, and then that will work. But the thing with the protected DMA bus is like you need to enforce firewalls. So the firewalls, there are also two solutions to the firewall as well. One is like the IOMMU based, basically the hypervisor can come into picture. So Qualcomm has the solution of the hypervisor that is enforcing the memory protections for all the devices. And there are other solutions, like I mentioned, there is a IP block sitting in front of the DRAM. The IP block that is sitting there has like very minimal sort of support for very discontiguous pages. Like it can't work on like many discontiguous page ranges because it has a specific table basically that is limited. You can have like say for example 100 entries in that table, not more than that, which are enforced or protected. So yeah, really we would like to see a use case for dynamic memory assignment where basically you allocate pages from the kernel range and you lend them to the firmware. Basically, to the firmware means to the secure side of the CPU. And once you lend that memory, you need to unmap from the kernel side as well. So right now, we don't see an API in the kernel that can allow like a normal kernel pages to be unmapped dynamically. So that is something we are looking forward to and trying to see for a solution there. So right now we have this protected DMA buffers being supported by the T subsystem, but we have a big to do here. So right now we are using this DMA alloc pages. So these are just kernel pages allocated for the DMA purposes, but we don't have a way to unmap them from the kernel. So once they are lent, we are just so any cache speculation, anything is just going to crash because the memory firewall would be set up after this point, and it's not going to work. So it will work in case there is a hypervisor, and hypervisor does the stage 2 unmapping. But if there isn't a hypervisor, then it's just going to crash basically the system if there is any cache speculation in there. So what we really want to achieve is like for this dynamic page allocation, a no map kind of behavior for this dynamic allocations basically. Yeah, the heterogeneous memory management, I was just looking at the subsystem. I see this API that says exclusive access memory for the devices. And so it's currently allowing the user space memory to be to be exclusive access for the device. But now I'm looking at the memory that is allocated in the kernel as well for the exclusive access for the device. Maybe we can extend that, or what we are looking is like page and map call chain of interest. That is, you can see in the kernel, this is the call chain we are mostly interested. Any other riders we're open. Yeah.
One of the items with this HMM approach that you're talking about versus like what you're used to, for example, for what we call APU approach in AMD, is that this memory always needs some sort of like backing store in regular memory, right? So the thing is, whatever's located in there would be pretty much like then put back and forth. Is this something that is, from your point of view, acceptable? I'm curious about this, like using HMM for that approach.
Yeah, I see that if there is any access from the CPU side, it's going to get that from the backup. And then, so basically what we are not worried about that CPU is going to access that memory at all, but we are worried about the speculation that can happen during that time. So
when if you use memory device private, you don't even have that problem. CPU will treat that as a private device memory.
So what I'm coming at is like what you are saying is like we need to migrate that to device, right? For every memory allocation, all the pages we have, we need to migrate that to device, right? So basically, we need.
Sorry, I think you'd have to migrate it for device private because it's completely, it's just a fictional page almost. I sort of wrote the device exclusive side code that I think you've just found as well, but that was very specific to user space mappings, as I think he mentioned. It sounds more like what you need is something that will actually unmap the page from the linear map, which to avoid CPU speculative access, which had similar bugs come. I don't know of any good solution off the top of my head either, like the device private stuff. It requires migration, which defeats the purpose. and the device exclusive is very, very user space driven.
Especially here, there would be multiple devices involved, so we need to migrate for every device problem. I don't know. I haven't looked at it.
I'd be interested to think about it. But
so I'm working on a patch set that adds a GFP flag that lets you allocate pages from the normal page allocator that are already unmapped, and it takes care of arranging them in a way that optimizes the TLB flashes and stuff. Which sounds like it might help you, but I'm not sure I understand why you can't just use the normal page allocator and then use like set direct map valid. So there's an API that just, it might not be very efficient, but you should already be able to do that. So maybe I'm missing why you can't just do that.
So there is an API like DMA alloc attributes where you can set no kernel mapping. So I'm interested to hear about whether that API is memory efficient on the similar term like you allocate from the system heap. So all the pages that are scattered, whether that also allows the scattered pages to be allocated if the IOMMU supports it or not. So
The use case, but if you integrate this deeply into the page allocator, then there shouldn't be very much scattering because the whole design of the page allocator tries to avoid that.
Okay.
But yeah, maybe we can chat in the hallway.
Sure.
I probably don't understand the problem well enough. So.
Okay.
So I guess just to be clear, you kind of need these pages like completely unmapped from every page table on the GPU, which I think is probably, maybe that helps answer your question, maybe? I'm not sure.
Are you saying that you have to like synchronize it with the IOMMU and the IOMMU also has to unmap it?
Yeah, yes, unmapping is like from the kernel's page table only, basically. Yeah, IOMMU would be there as well, yeah.
Yeah, I think maybe I can help. Yeah.
Yeah. Okay. Is there any further questions? Okay.
Okay, so the memory protection is normally, I think, in the two cases which you discussed. One is using the IOMMU and hypervisor doing the device level memory protection. So why are we actually using T framework to do that? So it's nothing to do with T framework at all. This API seems to go via TE APIs. And is there a plan to abstract it in a way that people can not use T framework at all? Just go.
So yeah, I was recently chatting with Dan as well about confidential compute use cases maybe in future. So yeah, there would be use cases that will come up because certainly we would be having confidential guests as well and the devices and not the host be able to access the memory, and only the guest and the devices would be able to access the memory. So yeah, there would be use cases, but as it happens, it's going to be an evolution, I would say. When the use cases come up, then we are going to evolve from there. Yeah. Okay, that's it. Thank you.
Our last speaker is remote. John, can you come on camera? There you are. And you should be able to take presenter on your laptop and present. If you in that bottom left corner, there's that plus button, and you can say take presenter, and then off you go. Oh, we can't hear you.
Hear me now?
Oh, now we can hear you. Yep.
Okay. Sorry, it's not my good mic. It's my AirPods, but it'll need to do. Okay, so let's see. Am I the presenter? Let's check. I am. All right. So hi everybody. So I know a lot of you. I'm John Groves from Micron, developer of FAMFS and also co-chair of software and systems at the CXL consortium. And this is going to be an update on FAMFS. a lot of you I know what it is. At the end, I've got links to quite a bit of detail because there's not enough time to do a whole overview on FAMFS. I'm going to talk about some new learnings on use cases, the roadmap, and the upstreaming plan. So one quick slide on the background on FAMFS. Stands for Fabric Attached Memory File System. It is intended to address shared CXL memory, because with shared CXL memory, you can't just give it to Linux. You can't make it online, because that's Linux can do whatever it wants. It doesn't understand another Linux instance also having access, and it starts by zeroing it, so that's a problem. So shared memory surfaces as DAX devices, and then FAMFS can format the DAX devices as file systems. And multiple hosts can mount the same FAMFS instance. I see a typo. Singe means single. And memory map files provide byte level access, so that, if you've got data sets and files, you can put them in FAMFS. If you happen to be publishing them and then sharing them without mutating, you've got no cache coherency issues. And read and write are basically memcopy. Now, there's a bunch of limitations. The only one node is currently allowed to create files, but if it makes sense, you can allow every node to mutate data in files. Although the early use cases that we're seeing are largely not a lot of concurrent mutation. But the core insight behind FAMFS was, oh crap, this shared memory stuff is becoming possible, and it's going to be hard to use because you have to map DAX and come up with a whole way of managing it. But that, hey, wait a minute, we can do this as files, and then quite a bit of stuff will just work. Okay, and the first patches went out in 2024, so we're coming up on 2 years. So upstreaming status, the goal was this year, but now the goal is next year, hopefully before the middle of the year. And there have been some DAX challenges. I think I see Alistair in the room. You did a bunch of nice cleanup in DAX, and it until basically about a week ago, FAMFS was broken past 6.15. But I finally crawled through all of that, and it's definitely, there's a bunch of improvements in there, but it broke doing the FS DAX thing with dev DAX. I've got a kernel now where that's fixed, and I don't think it's fixed quite in an upstreamable way, but I see how to do that now. So that's a big relief for me. Let's see. So the next FAMFS patch set is going to introduce FAMFS mode of DevDAX, or maybe FSDev named mode. And the difference is the whole folio initialization and ref counting strategy is different in DevDAX from basically FSDAX mode of PMEM, because what FAMFS does is it piggybacks on the fact that FSDAX was already a thing, and it just basically does the same. It's got its own mapping metadata, but it maps file data via FSDAX in the same way that XFS and ext4 do. So, and one of my recent realizations, but it's a nice improvement, is this relatively recent API DAX break layout final. I sort of woke up and understood that a few days ago, and it's FAMFS will be compatible or compliant with that, which basically, as I understand it, and if Dan or Alistair wanted to pipe up and tell me that there's more to it than this, clearly that will stall inode eviction and therefore unmounting if by any chance there's a file that's got that's a DMA target, that kind of thing. And that's, I think, was a hole in FSTax broadly before. So my hope is that the next patch set's going to not have to have the RFC tag on it. We'll see how that goes. But so that's where we are with the patch set. I wanted to talk about the use cases a little bit because, you know, the starting insight was just basically shared memory is going to be really hard to use if we don't have a way of making an existing access method map onto it. And so there's quite a lot of software that uses data and files, you know, databases, RocksDB, but lots of other stuff. Graph analysis is turning out to be a really interesting use case for this. And some of our learnings in looking at graph analysis are that, you know, the superpower of memory is low latency random access. If it's not prefetchable, if you can get a working set to fit in memory, there are big advantages. And so, and when we're talking about non-prefetchable workloads that that are big, you know, one of the things we do is we go, oh crap, but the CXL memory's, you know, got about 5x the latency of system RAM, and it doesn't have as much bandwidth, right? Well, that's true. But where this looks really interesting is with data sets that you just can't fit in system RAM. And so, can you see my mouse pointer? I'll assume that's that. Yes. So this diagram on the right, you know, system RAM, 100 nanoseconds unloaded. They're about disaggregated memory, even behind a switch, 500 nanoseconds, so 5x. But if you can't fit a working set in memory and it's random access non-prefetchable, the next step is like NVMe, and current generation NVMe unloaded latency is 50 microseconds, which is 100 times higher than the CXL switch, you know, with one switch hop in the current technology. Now, all of these things should improve a bit, but or should improve over time. But I'll take 100x whenever I can get it. And so let's see. So here's an interesting exercise, and it highlights another thing that was non-intuitive for me. And this is a graph analysis workload running on a 4-node cluster with the graph is about 4.6 terabytes. It's in FAMFS. The graph software just sees files and M-maps them. M-mapping the files is one of its native modes of operation, so that just worked. And we do a staggered start of 4 nodes running basically the same workload, but with a random starting point on each node against the same data in FAMFS files. The graph analysis software is from a company called Pometry. And what's fascinating about this is that you can see it really well in this graph that they don't interfere with each other's performance at all. And why would that be? Well, it's because graph traversal is last level cache misbound in the extreme. And so, you know, CPUs are spending a fair amount of time, you know, stalled waiting for cache lines to load. But that's still, you know, we haven't measured the loaded latency here. So it's loaded, it'll be higher than 500 nanoseconds, but it's still vastly lower than 50 microseconds, which is 50,000 nanoseconds. And so we're seeing things like workloads that if you had to demand page take like 7.5 hours, and if you can put it in CXL memory, it's 15 minutes. These kinds of improvements. And so,
John.
yes, sir.
Hey, John, you got 3 minutes.
Oh, okay. All right, I'll move on. So, yeah, roadmap. Hoping to get upstream. That's going to be a kernel patch, a libfuse patch,
We
and a
have a
DAC
question.
CTL.
We have a question in the room,
Oh, yeah.
John.
Sure.
Hey, and not necessarily on this slide in particular, but the FAMFS is basically a scale-out based. It supports scale-out interconnect. But what are your thoughts on scale-up interconnects? Let's say when we have UA-Link connecting accelerators across compute nodes, is it going to support that kind of architecture? When we have remote load store atomics across the scale-up interconnect. .mem
So
copy.
I think so. I'm haven't had the time to stop and look at UE-Link very carefully, but FAMFS is a scale-out way of organizing what files map to what memory. It's not CXL specific in any way. So I'm guessing that you could access over UE-Link if we can agree on basically FAMFS maps offset, an offset in a file maps to an offset on a DAX device. And so it wouldn't even necessarily have to be in the context of somebody accessing through UE-Link a DAX device, but it has to be a device abstraction.
Got it.
Yeah, it seems to me there's broader potential uses.
I have another question. So for the cases of where you have hardware coherence methods would that facilitate FAMFS going beyond the mem copy and kind of like the read mostly scenarios?
So that's a really interesting question. And so FAMFS does software manage cache coherency for its own metadata. And its metadata is basically a super block that gets initialized once and a append-only metadata log that gets initialized, and then there's and then only appended. And where I think hardware cache coherency would be useful more so than for the FAMFS mechanism is for the users of the files, because cache coherency is not automatic for them, which is why we're seeing the sort of publish and share model making a lot of sense, because if you can, dump 5 terabytes of graph data into FAMFS and then, flush the cache one time as you're copying, and then nobody's mutating, or you're carefully controlling that, then you don't have to worry about cache coherency.
Hey, John,
I don't know if that answered the question.
I'm going to ask you to give a wrap up here, because you're sorry to squeeze you in the last person before lunch, but yeah, you are staying meeting us at lunch. But
okay,
yeah.
So the presentation's online. There's some links if you want some detail about it. I'm happy to have people reach out to me directly if you have questions. And go team. I'm going to try to get this upstream this year. It's not a whole lot of code in the kernel. Most of it's in user space. So, okay.
And yeah, and I'll put in the chat. But we also have a CXL call, and we could do maybe a follow up FAMFS thing at that call if people are interested. But thank you for joining remotely, John. Appreciate it. We'll see you.
Thanks, guys.
Okay, now lunchtime. Thanks, John.
I'm super thankful for my family.
Yep. That's what she's doing today. Yeah.
So adorable is nothing. Perfect. My wife was probably more my way about this. I'm happy when it's over. I know it's important. I understand all this.
Right.
And that she does the right thing. Everything. That can be perfect. Whoa. I'll try this on my way back. I never heard about it. A lot of left credit.
Yeah, I understand. Oh, nice, nice. I'm so glad.
She's a process.
It's like, because those days, it's kind of unreal. Right. Right. Yeah. But it's happening over many weeks, so it's a bit too long.
There's a lot of things. It's like I wrapped it around going to a foundations. But I just ready to the GitHub and it does support me.
Mine.
kind of what we also did.
Now we all have that.
Right. Yeah, it's all right. I had a very good. I had a very good. Yeah. It's like we should not do this. And I was like, I knew that. I knew it. But I was like, wait, there's about three other bars. Well, he's like, we're not bringing it up in that discussion. Because he wasn't. But I can talk to him again. And what this essentially does. And did is, let's say you had some specific equipment, and you had it, but it was otherwise, unless someone explicitly asked you that, it's not touching. Right? Although, so this is so I'll lay out what it means for in the page application. A page is in a zone, a zone is in a node is in end memory, and the default memory policy in the page allocator is if the node is in end memory, I can do whatever I want. So my callback allocations, your motion, what if we can make a page allocator allocate from an SVM or an SP memory? And you have exclusive where if you don't use the flag, they all current users. You can never get memory from SP. But if you have flags, you can only get memory from whatever. Exactly. I was surprised. But we kept it. And I just, these are the areas where I don't have any visibility. Yeah, the main of my policy. Not sort of, but you guys have done to some extent. Engagement and building stuff. Well, is it the stuff?
Yeah, I mean, this is from like, it's almost like a contract. Producing that, they have instruments. Use this space to access
even if you have, you still have to manage the permission of the mappings on those.
I remember. There are more details than expected.
So the way you have it.
So you just you go replay this. Well, you don't have to use it as an fire and everything in the bed was like, I do also like their It's like what, you know, like a lot of companies do right now, you know, are so busy that it can be hard to grow it sometimes. So, and you will see that. The only thing I can say about say Mark instead of just throwing it in there. And so that's, but I did that, David pointed out this is not good, but we can mark those notes as needed. But what I'm getting at back to the kernel, say you have gas, then it's pretty wrong, right? And so this is the perfect case to try this right now and say, hey, I'm not isolating it, and solve those problems. You'll be happy with it. My point of view, Yeah, the only difference is you have, the way I am going to serve it is, so you have two of the best memory devices and accelerators.
Yeah, that's
Right.
it's a little confusing.
Well, yeah, okay, so here's exactly the one, right? What I have been trying to track the use case that I have some visibility is that, well, it's you have some form of access control that you want to manage the right. So the GPS and obviously the callback allocations that are in the one very specific situation. And it's when I go to allocate or when I go to write, if there is no memory left, you basically that's a long term. So what you I mean, but so like what you need is an interposition on right specifically. So you need to interpose on right. You can't do that if the page is just happens, the page is right. And so my point was the actual place is allocate it and then check with some component to say, I have a page. Is it safe? Like what is the compression ratio right now? In the worst case scenario, can I actually still wait?
It's like it's not just this year,
I don't want to catch the rights. I want to catch, like, the goal should be you actually really just want not necessarily cold, but like relatively cold. If it's compressed, it's going to be high latency. So you're not going to want high rate throughput memory on this device. So if you chop off the write from the page table and interpose on the right, you promote on the right, and now you have uncontrolled write access to the page. In the meantime, everything on that device is still mapped out, and you can access it without any additional interposition. That's what I implemented with this. Right. So like basically and then you would check in with the device like is this safe? Or to check in with the driver, is this safe? If it's not, you're like, cool, keep off replay. Yeah, I mean, this is right, or like we can use those devices to prevent kernel code from that's a whole different. That's a different.
Why we can't just use that device.
You probably can. The only there's one very specific reason. Yeah, the one specific reason for that is that the page out.serve does not enter. But we can change.
Yeah, but we can change. Kind of go to that thing.
And so there's a variety of things, and that's the implication. But I think the Willies of the world happy. No, I'm serious. To make them happy about this, it has to not. I think it has to not have men policy can't use men policy to manifest, right?
Okay, that's an interesting discussion, because that's kind of where I'm trying to hold it.
Yeah, well, because it was there. Yeah. Well, and I think we can draw a straight line, like for unified landscape. I think in theory, you can draw a straight line to, as long as there's no other conventional method on the node that has the binary SI, you can probably just go, okay, then this node goes in and memory and SD memory. Now you got
I mean, you can find it
and it comes
anywhere,
down
but
to
I feel
like,
like it's a
them
standard
driving to decide how.
like us versus them. Yeah, that's probably why they do
Basic operating systems, right? Like isolation is everything. Can't see how the plumbing works right away. I know the reason why I hesitate to say we should meet it's just like I in the actual use cases on top of what What I experienced the past 2 years is that if you propose having separate for more intelligent allocator and user space, you won't get there. Because that's the way DAX was originally proposed. They were like, we're gonna have a DAX device. You're gonna map the DAX device. And then, okay, we'll convert the DAX device. And then that is no problem. And so if you take the pain out of allocation, and now you simply have a line that says, this is where it's like, maybe we have it, like we have a gym, this line says, you could have a user that says, I give me this. And I think that's not unreasonable, but I think that's where you're gonna kind of push back. Yeah. But at least it's generalized on a particular.
I think it's also like people want to get like it is the thing that distributes power, I think. So and it's something that getting powerful. That's where.
I mean, I don't see the, well, yeah, I guess this is specific. to your use case. And the way I would say is, I need to understand the code that we are describing. I need to see the code that you're describing. I guess, the way I describe it, I can imagine a very simple
Exactly. I mean, I think that's, it's the same thing, but what solve some work. Because that's where the talent.
and then allocate memory, and then on default, the driver goes SP, GFP, SP, give me a bit of the but, yeah, except that it's like 10 lines of code instead of re-implementing a whole, right?
Which is some reason why.
Yeah, of course. So that is, for. MFT, MFT is confidential. And it like unmaps the memory entirely, so that user land can never, there's all that. But then they're interesting. Right. But that was specific. Specific to my use case would be, so here's the example. You have like a file manager kind of standard. And you're like something in between that interposes to say like, oh, my device has a bunch of special ways that it wants to manage memory. Like if I allocate a bunch there's it doesn't care about it. You get a page and but you may have some. So actually, my thought on this is the initial it was never been directly accessible. Instead, utilizing emotional. So all the turn mechanisms, it would say, hey, I found a cool page. Push it to the compressed memory. The compressed memory component, all it needs to know is that it has a URL. And then it just devotes a page there. And chops off and makes it boom. All of this, yes. Well, this is well, like that is like the ultimate policy. You are isolated from everything, right? All of your. When I grant some of it. Yeah. And so this is my point, like the trust RAM interface would be a kernel internal only interface that manages a trust. No, but this is like, this would be my use case. I demonstrated it on the patch set with Z-Swap, where it's just like, okay.
But it's all that sharing.
In this case, yes, but this shows you like there are two wildly different use cases that want the same thing. Let's go do that thing and then let you guys do your thing, let you guys do your thing.
Well, yeah, but this is actually quite a there's only about here and stuff already.
Does some of that,
does
like
everything drive the baseline?
Right.
And
and again, I'm not sure it agrees here as well, but then every IT has to implement pretty much the same thing in order to do that.
yeah, you're talking about, but see, this is where we need a user space.
Yeah.
API.
Right, exactly. But I think you can do that.
You can maybe do it.
Yeah, I think this can be done. And I think and this is what I said upstream of Fusebot. I think you can't get the core isolation piece ships. You can't do any of these.
Yeah, fine, we can work on that part, and then make sure we all agree on that.
Yeah.
That's right. And so like, some of the
I'm
other
trying to get that about harder now, and so I'm gonna ask him like, you know, what are.
And so, like,
could theoretically, is one time, is this, you know, a few days after that.
Yeah, in theory, well, other than the fact that page out does. Yeah.
You could have page out.
In theory. Oh, and I actually said, I think we could reuse zone devices.
Well, I think it's early, like,
And it's just like maybe GFP SP node or GFP SP or whatever flag you're doing allows zone device.
Yeah, I'm not saying all that advice, I just want to make sure we're not adding like.
Zone, yeah, no. And like there were two concerns. There's two, there were two concerns, and Dan said this, he goes, is this generalized and having like an infinite number of n nodes? And I was like, no, like if you create an SP node, you should know what that thing is for, and if you didn't create that node, you should not touch it. And maybe you have node types that track. The second thing is zones, no more zones. No more zones. It's either going in like, probably zone device is the right place to put it.
Yeah, right.
Maybe there's another flavor of zone device. Probably zone coherent device. And I think the important piece is. Right. And I think very specifically, and I just thought about the all of the plumbing for what do I do when I run into a zone device struct page already exists. Right? But this is the point, like, all of a sudden, okay, we might want that for this. It'll just be, like, instead of going to over here with device migrator, or whatever it is, it goes to the SP node management system.
But I mean, so most of the time, the zone device page.
Without the brewery and everything.
But no one is giving any lies if you wanted to reclaim.
I mean, what kind of
Yeah. Well, they could implement that, which is like.
I think the core concerns are, let's consider like, you guys have it mapped into page tables with the right bit chopped off. And if you want to do something special, you know, right, and so like, that's the whole like pages. And then it says, instead of doing do system fault or do page fault, it does like.
You want to collect them.
really when something tries to slack to it. Well, I think at the moment, I think Mark just makes it completely inaccessible. There's no reason.
Yeah, the thing that you also know that this differentiate between the for the new system, but yeah.
I don't think that really differentiating on the price to change it.
The thing is that these for interior, I think it's done the same thing. Is that when you page inflation you have that, then you can actually have that become on the device support.
Yeah, we can do all that. Exactly. But that doesn't shift. I'm
not saying the main problem I was saying is one is that isolation part, the other one is essentially the residency, right?
Yeah, which the residency already kind of like I think most of the residency stuff already.
Yes. However, that's what I was saying is that mostly committed that committed never did that. So that memory from you already have that. Memory like committed in that relationship like that, correct? From that, like you wouldn't almost memory, but have to read what's not home. So and then having also like that the right block called H ball. Then that's the natural way to also handle that. And you can use all of them.
You use all of the existing mechanisms. You can still use reclaim just with and that's the at least for the compressor. That's yeah. So I think that America does. So I did have a question. Well, that's the thing. I was like, there's two different pieces here. There's the allocation and free aspect, and maybe some of the features like that. And then there's the core services that M provides that you may or may not want based on what your thing is. And so it's like, and create policy on top of that if we have the isolation done. And this is why I was just like, MEM policy, the component is not sufficient for that at all. As designed, I don't think that policy will be extended to fully split. All that policy cares about is yes, nothing. That's it.
So all the other that part is pretty much that.
And I bring this up in my talks. MEM policy is completely ignored in many cases.
For that.
No, like anything that touches migrate completely ignores the law. It just does not. Yeah. And so that's why MEM policy is dead. Yeah. But at the end of the day, this is like, oh, you make your like still just want to use MEM, right? Or MEM. But you can still, what's funny is food mallet just turns into like a wrapper around a page, get free page call, which is really good.
It was interesting though. They're very good.
I mean, just
some arguments, but in the hearing, like.
Yeah, we can talk that.
I agree. That's the problem. It seems like, he was having a tough time, but he's being Robert. And that's right. Yeah.
Well,
it's interesting because usually, he's very good at that, meaning like, I'm very happy for the judge sort of thing, but you're just like, almost, right.
Ultimately, the goal should not be better because that's what our patient that's so, but I think I want to work or by a mixture of both, right? And the replacement would be defining of what is done with the memory.
Yeah, because most regions are going to fast time.
That would be
never solved. I think that's really
yeah, this is use cases, and it's just like I will close out the.
But it's very
well, it's but again, yeah, it's the same mechanism.
It it's the user space programming.
Yeah, and that's the point where I'm just like, I can see your space as well. Weird, gross, go to your, go in the corners. LPC.
I heard none of you were running space programs. Totally like, that's to me what's the big thing. Very validating.
My plea for people is, please don't make anybody go fucking drive. And for, really sake, please keep this shit in the bucket. Right? Or like, if you can make it generalized, compressed brand components that can manage these things without it having to be technology specific. That's still.
I think most of the stuff is in a box.
Yeah, absolutely.
And you could write a driver today and somehow pull back from the shrink. Hey, we need shrink stuff. Here's a driver that migrates to here and
or
make it 3 days. But you want to make that big.
You implement, it's like you implement the policy, you can either do it one of 2 ways. Either the existing shrinker code completely skips it all, and the driver just says, hey, also include this mode, and then do the generalized thing, or a callback might be.
Yeah, it's kind of the way I see your use case could work. If we didn't change it, then all you really need to pull back some money.
Right.
To basically go. Okay,
And this is
let's
like every
allocated migrate this virtual address to that.
I just need a callback from the X code. Like it's an insert X, like if you reclaim, migrate. Pick a place, like, and this is where it's like, the use cases have to drive how this thing actually evolves. But the isolation piece.
Oh, yeah.
is-
But I guess I'm not saying you got
it's just a page alloc has no real policy.
Right.
It's just once it's in there, it's in there.
But like you can do cool. You can.
That's like what the algorithms make.
One is like precisely what would be able to control how don't get goes down to and the other thing is essentially what you I think you just hold like
Yeah, I mean, we have to get.
No, it's.
Yeah, well, I think I did most of the work. Previously, I had tried to actually, you got a good background.
The room was surprisingly full.
What did you witness this?
One, I guess stupid observation. Because the memory is his own device, and because the drivers or whatever. Good is migrate and memory to be able to say like, oh, this is HBM memory, but it's not being used, so just bring it up to the variable. Now it's, general purpose memory. And like, it's just a quirk of the system, but it is. Yeah, well, yeah.
By definition, right?
But so that's a good point for like, everything I'm doing right now is based on the whole, but so we need to support fitting into everybody.
That can encourage you, because there's something else you have for a long time. Device. You want to upload one,
but shouldn't that Like the driver's seat is full of just.
Well, yeah, that's what it comes down to. What is your model? Like, and the way that we're sort of trying to do that is everyone has devices thinking like page model.
Yeah.
And then you don't have to think from. Because the problem with pinning is essentially you have say an NVMe device that has input from it can't store page models, and then you have no way of that. There's no mechanism to drive it. Internal operating go and say, hey, I'm putting that page, and that's because there's no mechanism in the hardware. Stuff you do.
We need precedent. In terms of like the implementation that would also have to happen in all those cases. That is actually something where it would like to assume for our point, people will see that and assume, for example, certain behaviors of the cache evaluation, etc., or of the backward. All those arguments made, for example, and particular identity properties, etc., then would be maybe drive your code, when you do this method and call it driver, etc., consume a certain latency, etc. So,
well, it's the policy piece in particular elements and removes it from, like, rather than driving the policy code into Linux MF, it pushes the policy into whatever the heck knows what this thing is.
Yeah, but again, ownership of right. That's the thing. I think about the operating on the memory. It's not only one later, but one then that is something that has been a abstraction of what the effect is. I think
yeah, like what if I have
lawyer called
now, if one of those things has a special mode that does the special thing, whatever, does all the migration. You're on your own. But this is where you kind of get into like the specification now. For the, I think like, CXL is a pretty good. The CXL subsystem has a pretty good track record. Oh, it's neat that your device does X, but unless it makes it into the specification, you're not going.
Yeah, no, I understand. I just really like this. The reason why we have not see that with that. Yeah, is that again, there's a lot of publishing of how things work that may or may not necessarily that out on other data fabrics than what CXL is, but like they do other things.
I don't think there's anything to say about that.
So, well, there's actually a about you have to see that. Trigger the event of that connection.
Yeah, you have to go through the mailbox.
And that is something questions. Yeah, but that is actually something that is
I mean, in my head, because CXL exists, like you have the EFI memory SP set. You get a node that it's.
And you have all like all the information that you upload that the caching policy there.
Well, I mean, put it this way, all of that information can be driver provided based on whatever source it comes from. Doesn't necessarily.
Maybe it is.
I mean, but that's like, come on. Like, that's always the case.
No, it's not always the case. Like, this is great. So Windows,
Windows.
And on Windows also, like, if you have well, like, not provider, electronic, you are operating the VM. So, well, what do you know what they have to
Get those guys in this room to talk about the problem, and I'll hear about it. Okay. But seriously, like, I can't speak to that.
No, of course. The thing is, like, for my point of view, that look at the systems that you go without cross dependencies, simply like the overall architecture.
I think from the baseline of can we provide isolation and limit the exposure to external components, including user land from the start, not not necessarily always, get those, gets those people in the room to have that conversation about how the best solution is designed. But unless you can get that conversation, as part of the bring up learning, like, as part of the, your work that you get, the one RFC I did, I do not have any compressed memory stuff. I have a into Z-swap that demonstrates that. Okay. And then I'm gonna push that stuff off. So it's like, but the vendors.
I think it's also the other one who put a lot of work into this people working on what is the starting point
Let's
to
get started. And then I want to get, say, 2 or 3 vendors.
Not so much, but I mean, our stuff is similar to, like, I mean, I'm very over here. You know, we still have LPC guidelines, so it's like, it's not like CXL flag or standard, but it has all of the same.
My thought is, you want to be driver.
All right, yeah.
And that's whether that driver. Slow memory. I just want an easy way to do it. And push the policy for the rest. But then I got in, that everyone wants.
So what we do is we just present that. And that's the control link, and then you have this weird memory thing that hangs around in the background. I don't know, like, I haven't, like,
I did when I was started, even I have an RMC.
PCI means good, but then you have to like figure out how to, you know, it's all my identity or even they've got to expose user and you just want to get to that. Then you run into these other issues.
What's that? I don't think it deals with your legacy.
Using CXL. I lost that. Right, so you can see exactly like the memory. In relation to that, so that's sort of. Yeah, I'm worried about that, which is cursed as well, the virtualization thing, because one of them.
Yeah, no, that's like, I mean, there's very much. That's the deal. So it exists.
Right, that's what, that's what. Because we should trying to get outside of the ecosystem. In a sense, right? Like, it should be used.
When it goes to continue, like, what they're trying to do right now is, oh, CXL goes all the way up. And it fails at some point, CXL stuff, but it's still no. SP memory there. Default
We haven't had
maybe
people that they use
systems out there that are going to be online.
So, yeah, I don't know. Yeah, I mean, the other difficulty is involved in sort of setting up, launching jobs or
But also, there are parts where and eventually, part of it is not root board, part of the hierarchy. Is the hierarchy. Yeah, they all have different cycles.
I'm hearing these things myself like this, and I know things are built on.
So it's like,
yeah. It's just ends up appearing in some sort of just
like so, yeah, like
I had a PC, so can I ask you a question? I had a PC, and I got the hardware by what I'm sort of for it to be six. What would you have to do to make some arbitrary PCI device with, say, a large piece of bar 1 memory space? What do I have to do to make that look like a CXL device?
And then the prevailing actions from the community has been to show. So like, there's a fundamental first
Right, to get the specific sort of context space.
Which probably is the code is there, right? So how do I, how is this problem, or how the whole issue to address this problem away from that? Yeah, and I think the answer is. That's what the until it's proven out, and then you just have all of the.
So I'm very happy. It's just where the best result. I'm not sure if I'm pushing it. Yeah, it's kind of that concrete.
It does have configuration. I'm still working about that.
No.
And I think right now we have a bunch of interfaces.
Not on memory, but
online all of that because the core has said, don't hang out on this issue.
Yeah, this computer, just really quick, high latency. I think it's about us putting it. Yeah, I mean, yeah. I remember your face. Yeah, you know your face. Stick. There's a lot of us here this year.
You might not know.
Maybe we should talk so that I can find out what we're doing.
Exactly. Well, that's the hard part, right? Yeah. But you know that it's already-
Yeah.
Okay, yeah. There's a nice aspect. It's not gonna work for every use case, but it is possible. See you in a bit. That's a full head for everything on the MSN. Hey, we should do the thing everyone thinks we should never do. Let's go. This is very fun. Hey.
Is it this one right here? I think it might be next to it. Here. Open that one. We're in the.
Sorry. No.
So I try again. That's what I did. So I just pressed the bumper and then so yeah, I did have this issue. I do have, yeah, sorry.
I feel very, you're executive director.
You are currently the only person in this conference.